Quine's Paradox. The sentence that describes itself. Imagine reading a sentence that by its very nature turns truth upside down. You follow its logic, thinking you understand, but then, wait, something isn't right. The more you try to pin down its meaning, the more it slips through your fingers. Welcome to Quine's Paradox, a self-referential puzzle that bends language and logic into contradiction. Consider this peculiar phrase: yields falsehood when preceded by its own quotation. At first, it seems harmless, just a simple sentence. But let's put it to the test. What happens when we place the phrase inside quotation marks and then follow its instruction? Yields falsehood when preceded by its own quotation. Yields falsehood when preceded by its own quotation. And there it is. The paradox. If this sentence is true, then what it describes must be accurate. It must yield falsehood. But if it yields falsehood, then the original statement must be false. And if it's false, then it does not yield falsehood, meaning it should be true. We're stuck in a loop where truth and falsehood collapse into contradiction. This is where Quine's paradox differs from the liar paradox. The classic, this statement is false. The liar paradox creates a contradiction through direct self-reference. Quine's paradox, however, plays a different game. It builds meaning structurally, using the arrangement of words rather than a simple true or false claim. It's like a logical trap hidden within the sentence itself. You might be thinking, this is just a language trick, right? Something fun to think about, but not something that matters in the real world. Not quite. This paradox has serious implications beyond wordplay. In linguistics and philosophy, it highlights the limitations of how language can define itself. In mathematics and logic, it relates to Gödel's incompleteness theorem, which proves that certain statements in mathematics are true but unprovable within the system. In computer science, self-referential logic plays a crucial role in programming. If not carefully controlled, it can lead to infinite loops or paradoxical errors in software and artificial intelligence. So, is there a way to escape Quine's paradox? Some argue that we should avoid self-referential language altogether, setting stricter boundaries on what statements can and cannot refer to. Others suggest that we need to expand logic itself, introducing a third category beyond true and false, perhaps undefined or paradoxical. And then, there's the approach of formal logic, where strict mathematical rules prevent sentences like this from arising in the first place. Whatever the solution, one thing is clear: Quine's paradox exposes a strange and fragile edge of logic, where words can fold back on themselves and turn certainty into uncertainty. It's a reminder that sometimes, even the simplest sentence can unravel everything we assume about truth. The Pinocchio Paradox. When lies and truth collide. Imagine you're standing in front of Pinocchio. He looks you straight in the eyes and says, "My nose will grow now." Now, you wait. Nothing happens. Or does it? If his nose grows, that means he was lying. But his nose only grows when he lies. So that means he was telling the truth. But if he was telling the truth, then his nose shouldn't have grown. But if it doesn't grow, then he was lying. And around we go, trapped in a paradox that seems impossible to escape. This paradox is a twist on the classic liar paradox, the famous statement, "This sentence is false." But here, we're not just dealing with words, we have a physical consequence attached to the contradiction. Pinocchio's nose either grows, or it doesn't, and yet both possibilities seem to break the logic of his statement. It raises a strange question. What happens when a contradiction isn't just theoretical, but actually has an effect on reality? If Pinocchio's nose is supposed to grow only when he lies, then what does the universe do when faced with a sentence that logically collapses on itself? This isn't just a fun fairy tale puzzle, it's a deep problem in logic, philosophy, and even artificial intelligence. If an AI were programmed with absolute truth conditions like Pinocchio's rule, How would it handle self-referential contradictions? Would it freeze? Would it break? In psychology, the paradox connects to the way humans rationalize truth and deception. Do we ever get caught in logical contradictions in our own thinking? So, is there a way to solve it? Some argue that Pinocchio's nose wouldn't react to predictions, it only grows when he tells lies about the past or present, avoiding the paradox altogether. Others suggest that the statement simply doesn't belong in the true-false system. Some things just don't fit into those neat categories. And then there's the idea that maybe the story's logic itself is flawed. Perhaps the rule about his nose is too vague, and paradoxes like this reveal its inconsistency. The Pinocchio Paradox is a reminder that language and logic can collide in unexpected ways. What seems like a harmless phrase can unravel everything we assume about truth, falsehood, and cause and effect. And if even a wooden puppet can break our understanding of logic, what other paradoxes are lurking in the way we think about the world? The Liar Paradox. A deep dive into the statement that destroys logic. The Liar Paradox is one of the most puzzling paradoxes in philosophy and logic. It arises when someone says a simple sentence, "This statement is false." At first, it looks harmless. But if the statement is true, then what it says must hold, it must be false. And if it's false, then what it says must not hold, which means it must be true. This contradiction creates an endless loop, where the statement is neither true nor false. This paradox isn't just a word game, it challenges our understanding of truth itself. Can something be both true and false? Or do we need a different way to think about truth and language? The Liar Paradox isn't new. Over 2,000 years ago, the Cretan philosopher Epimenides made a statement that started it all. All Cretans are liars. But if he was a Cretan himself, was he lying or telling the truth? This puzzle has fascinated thinkers for centuries, including Eubulides of Miletus, Augustine, Thomas Aquinas, and Bertrand Russell. Each explored the paradox, trying to make sense of the contradiction hidden within language. The paradox has led to major developments in logic and mathematics. Alfred Tarski, for instance, argued that paradoxes like this occur because natural language lets sentences refer to their own truth values. He suggested creating a hierarchy of languages, where truth statements belong to a higher-level meta-language instead of the same language they describe. Then there's Gödel's incompleteness theorems, a revolutionary idea in mathematics. Gödel showed that in any complex mathematical system, there will always be statements that are true but cannot be proven within the system itself. This is eerily similar to the Liar Paradox, because it suggests that self-referential statements reveal deep logical limitations. Some logicians have tried to deal with this paradox, using paraconsistent logic, a system that allows contradictions to exist without breaking everything. Instead of treating truth and falsity as strict opposites, this approach suggests that some statements might occupy a gray area between true and false. Beyond philosophy and mathematics, the Liar Paradox has real-world consequences. Artificial intelligence and computing face issues when processing self-referential statements, which can lead to infinite loops or logical failures. Legal contracts sometimes include self-referential clauses, leading to ambiguity that can make agreements difficult to enforce. Even linguistics and semantics struggle with the paradox, forcing us to question how meaning and truth are assigned to statements. So, how do we resolve it? Some argue that we should simply reject self-referential statements, avoiding the problem altogether. Others suggest introducing a third truth value such as undefined or paradoxical to classify statements that don't fit into a strict true or false structure. Another approach is to consider context. Perhaps the truth of a statement depends on the situation in which it is spoken. Some even embrace paradoxes as an unavoidable part of language, much like quantum mechanics accepts strange counterintuitive phenomena in physics. The Allais Paradox remains one of the most mind-bending problems in logic. No single solution has been universally accepted, and perhaps that's the most fascinating part. It forces us to rethink what truth means, how language works, and whether logic itself has limits. What started as a simple sentence has led to profound questions about reality itself. Barber Paradox, the confusing game of descriptions. Think about numbers for a second. Some are easy to describe, like the smallest positive number, 1. Others take more words, like the smallest number greater than 1,000,000, 1,000,000, 1. But what if I told you that a simple description of a number could break logic itself? Welcome to the Barber Paradox, a strange contradiction hiding in the way we use language. Let's play a quick game. Imagine we're looking for the smallest number that cannot be described in fewer than 20 words. Seems straightforward, right? But there's a problem because the phrase "the smallest number that cannot be described in fewer than 20 words" is only 14 words long. That means we've just described this number using fewer than 20 words, even though we said that wasn't possible. That's a contradiction. The number both exists because we just described it and cannot exist because its definition says it must take 20 plus words. Language just folded in on itself, and now we're stuck in an impossible loop. This might sound like a weird language trick, but it actually points to a huge problem in logic and mathematics. We assume words can describe anything in a clear way, but this paradox shows that some descriptions destroy their own meaning the moment we try to use them. It's like a snake eating its own tail, self-reference twisting back on itself. Mathematicians have been dealing with problems like this for a long time. Numbers are infinite, but words are not. If we try to describe some numbers too precisely, we end up in paradoxes like this one. It's similar to Gödel's incompleteness theorems, which show that some truths in mathematics can never be proven within their own system, a mind-blowing idea that shook the world of logic. This paradox isn't just a quirky puzzle, it has real-world consequences. In computer science, precise definitions matter. If a system runs into a contradiction like this, it could cause errors, crashes, or infinite loops in programming. In linguistics and philosophy, it raises questions about how language can fail when pushed to its limits. In information theory, it challenges how we compress complex data into simple descriptions. Some things might be impossible to summarize without breaking logic. So, how do we deal with it? Some argue that we should only define numbers using strict mathematical formulas, avoiding the messiness of language. Others suggest that we should be careful with self-referential descriptions, setting rules to prevent contradictions. And then there's the idea that maybe some concepts simply can't be described fully, that some things exist in a gray area outside of logic's neat categories. The Barber Paradox is a perfect example of how something as simple as a sentence can expose deep flaws in how we think about logic and truth. It's a reminder that language isn't always reliable, and that sometimes, even words themselves can lead us into paradoxes we can't escape. Grelling-Nelson Paradox. When words betray logic. Have you ever thought about the words we use and whether they apply to themselves? Some words describe themselves perfectly, like short, which is literally a short word. Others don't, like long, which is not long at all. Seems simple, right? But what if I told you that there's a word that refuses to play by the rules? A word so tangled in contradiction that it breaks logic itself. To understand the paradox, let's define two types of words. Autological words. These are words that describe themselves. Short, because short is a short word. English, because English is an English word. Pronounceable, because pronounceable can be pronounced. Heterological words. These are words that do not describe themselves. Long, because long is not a long word. French, because French is an English word, not a French word. Silent, because silent is not silent at all. So far, so good. But here's where everything starts to fall apart. What about the word heterological? If heterological belongs to the group of heterological words, then it must not describe itself. But wait, heterological words, by definition, do not describe themselves. That means heterological does describe itself. That's a contradiction. On the other hand, if heterological is autological, it must describe itself. But if it describes itself, then it does not belong in the heterological category, another contradiction. So where does heterological belong? Nowhere. It simply doesn't fit into either category. And just like that, language collapses in on itself. This paradox isn't just a fun word game, it's a serious problem in logic, philosophy, and mathematics. It's similar to Russell's paradox, where a set that includes all sets that do not include themselves collapses under its own definition. The same issue applies here. Some things simply cannot be neatly categorized without breaking the system, and the consequences, bigger than you might think. In linguistics, it highlights the flaws in categorizing words based on self-reference. In mathematics, it challenges how we define sets and logical structures. In computer science, AI and programming languages must be carefully designed to avoid contradictions like this, which could lead to infinite loops or system failures. So how do we deal with it? Some suggest that self-referential definitions should be avoided entirely. If a word starts referring to itself in a way that causes contradiction, maybe we just don't allow it. Others propose formal logic systems where contradictions are flagged rather than breaking the entire framework. Some even introduce a third logical category, beyond just true and false, for cases like this, calling them undefined or paradoxical. At the end of the day, the Grelling-Nelson Paradox is a reminder that even the simplest things, like how we describe words, can turn into an unsolvable puzzle. And if something as basic as a word can break logic, what other paradoxes are hiding in plain sight? Card paradox, a logical loop with a simple card. You pick up a card. Seems normal enough. Just a statement written on each side. You flip it over, read the first message, then turn it to check the other. That's when something strange happens. The more you try to understand what the statements mean, the more confused you get. The logic loops in on itself, and suddenly, you're trapped in a paradox. The front of the card reads, "The statement on the other side of this card is true." You turn it over. The back says, "The statement on the other side of this card is false." That's it. That's all it says. And yet, somehow, these two statements destroy any chance of finding out what's actually true. Let's assume the statement on the front is true. If that's the case, then the statement on the back must be true as well, except that it says the front statement is false. That's a contradiction. Alright? So maybe the front statement is false. If that's true, then the statement on the back must also be false, which means the front statement is actually true. We're right back where we started. No matter how you approach it, the two statements trap you in an endless loop of contradiction. This paradox is a close cousin to the Allais Paradox, the famous statement, "This sentence is false." But here, instead of a single self-referential contradiction, we have two statements that create an endless cycle. It also resembles Russell's paradox, where a set that includes all sets that do not include themselves collapses under its own definition. It might sound like a fun word game, but the card paradox exposes real problems in logic, philosophy, and even computer science. In mathematics, contradictions like this are exactly why set theory had to be rewritten. In computer programming, an infinite loop caused by self-referential logic can crash entire systems. Even in artificial intelligence, carefully structured reasoning must be in place to prevent AI from getting stuck in paradoxes like this. So, is there a way out? Some argue that self-referential statements should simply be avoided. Logic should not allow statements to define each other in a way that creates contradiction. Others suggest using three-valued logic, where something can be true, false, or undefined, making paradoxes like this fall into a special category outside of standard truth values. Another way is to break the chain entirely, suggesting that at least one of the statements is meaningless, preventing the paradox from forming. The card paradox is a perfect example of how language, logic, and self-reference can tangle together and collapse under their own weight. Something as small as a few words on a card can challenge the very idea of truth itself. And if a simple card can do that, what else in our world might not be as logically sound as we assume?
The Crocodile Paradox. A logical trap. A crocodile snatches a child from the riverbank. Just as the desperate parent screams for mercy, the crocodile offers a deal, one that seems fair, but is actually a trap. I will return your child if and only if you correctly predict what I will do next. Seems simple enough, right? The parent, thinking carefully, makes a bold prediction: you will not return my child. At that moment, the crocodile freezes. The deal, meant to be a test of logic, has backfired into an impossible situation. The question is no longer about the child's fate, it's about whether logic itself can escape the jaws of contradiction. If the parent's prediction is correct, meaning the crocodile was going to keep the child, then according to the deal, the crocodile must return the child. But the moment the crocodile does that, the prediction becomes false, breaking the condition. If the parent's prediction is incorrect, meaning the crocodile was going to return the child, then by the deal's rule the crocodile is not required to return the child. But if the crocodile keeps the child, the prediction was actually true, which means the crocodile should return the child after all. No matter which way you turn, the logic collapses in on itself. The crocodile is caught in its own trap, unable to logically follow through on its own rule. This paradox isn't just about a tricky reptile. It reveals something unsettling about if and only if logic. The idea that truth can depend entirely on predicting itself is deeply flawed. Similar paradoxes exist, like the Allais Paradox, where a statement contradicts itself by saying this statement is false, or the Pinocchio Paradox, where Pinocchio says my nose will grow now, but his nose only grows when he lies, leading to the same kind of contradiction. The Crocodile Paradox isn't just a fun brain teaser, it has serious implications in law, philosophy, and artificial intelligence. In legal contracts, self-referential conditions, like I will pay you if you correctly predict that I will pay you, can create contradictions that make enforcement impossible. In philosophy, the paradox challenges our understanding of truth and cause-effect relationships. If a truth is dependent on itself, can it really be called truth? In artificial intelligence, logical loops like these must be avoided to prevent AI systems from getting stuck in infinite contradictions. So, is there a way out of the paradox? Some philosophers argue that self-referential promises should be rejected altogether, meaning the crocodile's deal was never valid in the first place. Others suggest we need a third truth category beyond just true and false, one that allows for statements to be undefined when they break logic. Some even propose using probability. If the parent has only a chance of guessing right, the deal avoids the paradox. No matter the approach, the Crocodile Paradox reminds us of one thing: not all logical traps have an escape. Some, like the jaws of a clever predator, snap shut the moment you step into them, and when logic eats itself, we are left with nothing but contradiction.
Russell's Paradox. The set that destroys itself. Mathematics is built on logic, and logic is built on rules. But what happens when the rules contradict themselves? That's exactly what Bertrand Russell discovered in 1901 when he stumbled upon a paradox that shook the foundations of mathematics. A set is simply a collection of things that share a common rule. The set of all red objects contains everything red. The set of all dogs includes every dog in the world. The set of all even numbers consists of numbers like 2, 4, 6, and so on. It seems simple. If you can describe a group with a rule, you can create a set. But Russell found a problem hidden in this idea. Imagine a set that follows a very particular rule, the set of all sets that do not include themselves. Let's call this set Ra. Now here's the question. Does Ra include itself? If R includes itself, then it breaks its own rule. It's supposed to only contain sets that do not include themselves. But if R does not include itself, then it must follow its own rule and include itself. Either way, we end up in a contradiction. Ra both must and must not include itself at the same time. This paradox revealed a flaw in how mathematicians defined sets, leading to a crisis in logic. At the time, mathematics relied on set theory as a foundation for everything else. But if contradictions like this existed at the very core of math, how could mathematicians be sure that their entire system wasn't filled with errors? The discovery forced a rethink of set theory, and eventually, new rules were created to prevent such contradictions. One solution came from Zermelo-Fraenkel set theory, which introduced stricter rules about what can and cannot be a set. Another approach, proposed by Russell himself, was type theory, which arranged sets into different levels so they couldn't mix in paradoxical ways. Others explored alternative logic systems that allowed contradictions without causing everything to fall apart. The impact of Russell's paradox goes beyond mathematics. In computer science, logic errors like this can cause infinite loops or software crashes. In philosophy, it challenges how we define groups and categories. In artificial intelligence, systems must be carefully designed to avoid paradoxes that could break their reasoning processes. As strange as it seems, this paradox taught mathematicians a valuable lesson. Sometimes, the most dangerous problems come from the simplest questions. Today, thanks to new mathematical frameworks, we can work around Russell's paradox, but it remains an important reminder that even in a world built on logic, surprises can still lurk beneath the surface.
The Barber Paradox, a logical dilemma that defies reason. Imagine a small town with a peculiar rule. There is only one barber, and he shaves all men who do not shave themselves, and only those men. At first, this sounds like a simple guideline, but then a question arises. Who shaves the barber? If the barber shaves himself, he falls into the category of men who shave themselves, meaning he should not be shaving himself. But if he does not shave himself, then he must be shaved by the barber, which is himself. No matter how you approach it, the rule contradicts itself, trapping the barber in an impossible loop. This mind-twisting paradox was formulated by Bertrand Russell, a British philosopher and mathematician, as a way to illustrate a deeper issue in logic and mathematics. His work on set theory revealed contradictions similar to the barber's dilemma. He posed a question: does the set of all sets that do not contain themselves include itself? If it does, it must not. If it does not, it must. The contradiction exposed a major flaw in how sets were defined, shaking the foundations of mathematics. The Barber Paradox highlights a broader issue with self-reference statements or systems that refer to themselves in ways that break logical consistency. It has influenced philosophy, mathematics, and computer science, forcing thinkers to reconsider how rules, categories, and logical systems are structured. Some attempted solutions involve rejecting the possibility of such a barber existing altogether. Others suggest that the definition of his shaving rule is inherently flawed, making the paradox a linguistic issue rather than a logical one. Some propose more flexible logic systems,
where truth is not just black and white, but allows contradictions to exist without collapsing the system. Beyond logic puzzles, this paradox has real-world implications. In computer science, self-referential loops can cause infinite errors in software. In linguistics, self-referential definitions create ambiguities that can make language inconsistent. Even in law, some self-referential rules lead to paradoxical legal dilemmas, where a law governing itself creates contradictions that cannot be resolved. At its core, the Barber Paradox reminds us that not all problems have solutions. Sometimes, the very way a problem is structured makes it impossible to resolve. Instead of looking for an answer, the best approach is often to question the assumptions that created the paradox in the first place.
Yablo's Paradox, an infinite web of contradictions. What if I told you that a single sentence could trap you in an endless cycle of contradictions, but without ever referring to itself? That's exactly what Yablo's paradox does. Unlike the classic Allais paradox, where a sentence declares itself false, this one doesn't need a single statement looping back on itself. Instead, it stretches out infinitely, pulling you deeper into a web of logical contradictions. Imagine you're looking at an infinite list of statements, each making a claim about all the ones that follow it. It starts like this. Statement 1. All statements after this one are false. Statement 2. All statements after this one are false. Statement 3. All statements after this one are false. And so on forever. Each statement claims that everything that follows it is false. But what happens when we actually try to determine if any of them are true or false? Let's assume statement 1 is true. That means everything after it. Statement 2, statement 3, and so on must be false. But if statement 2 is false, then its claim that all later statements are false must also be false. That would mean at least one later statement must be true, but all later statements say the exact same thing. If one of them were true, it would contradict the others. We're stuck. So, let's flip it and assume statement 1 is false. That would mean not all later statements are false. So, at least one of them must be true. But if one of them is true, that means everything after it is false. And once again, we're back in the same contradiction. No matter how you try to sort it out, this paradox throws logic into an infinite loop. There's no clear way to assign true or false to any of the statements without breaking the system. This paradox isn't just a fun mind game, it challenges our understanding of logic, language, and truth itself. Unlike the Allais Paradox, where a statement directly contradicts itself, Yablo's paradox spreads the contradiction across an infinite sequence, making it even trickier to pin down. It's not just a philosopher's puzzle either. This kind of paradox has real-world implications. In philosophy and logic, it forces us to rethink self-reference and how truth can be structured over an infinite series. In mathematics, it connects to Gödel's incompleteness theorems, which prove that some mathematical truths exist but can never be formally proven. In computer science, logical paradoxes like this must be avoided in AI systems and programming to prevent infinite loops that crash systems. So, can we escape this paradox? Some logicians argue that infinite chains of reference should be restricted to avoid contradictions like this. Others suggest using multi-valued logic, where instead of just true or false statements can be labeled undefined. Some even try to mathematically reformulate the paradox using set theory to understand its hidden structure. Whatever the approach, one thing remains clear. Yablo's paradox is a haunting reminder that logic itself has limits. Truth isn't always straightforward, and sometimes, even without a direct loop, we can still find ourselves trapped in an endless cycle of contradictions.
Zeno's motion and space paradoxes. The fastest runner paradox. Picture this. The fastest runner in the world stands at the starting line. muscles tense, ready to explode forward. The crowd holds its breath. The gun fires. And according to Zeno, that runner never actually moves. Sounds ridiculous, right? But that's exactly what the fastest runner paradox suggests. Despite what we see with our own eyes, Zeno argues that motion itself is impossible. How can that be? Let's break it down. Imagine the runner is racing toward the finish line. Before they can reach it, they must first get halfway there, but before they reach halfway, they must travel a quarter of the way, and before that, they must move 1/8 of the distance. This continues infinitely, with each step requiring another fraction of the distance to be covered first. Since the process never truly ends, Zeno argues that the runner can never even take the first step. If every movement requires an infinite number of smaller movements to happen first, how can motion ever begin? And yet, people run all the time. They reach their destinations, cross streets, sprint to catch a bus. So why does Zeno's argument feel so logically airtight, while also being obviously wrong? The issue comes down to how we think about infinity. Zeno treats space as something that can be divided endlessly, assuming that an infinite number of steps must take an infinite amount of time. But that assumption isn't quite right. Think about a candle burning down. You could divide its melting wax into infinite tiny measurements, but that doesn't mean the candle will burn forever. Even though the process can be split into an infinite number of small changes, the total time remains finite. The same logic applies to motion. Modern mathematics clears up the confusion. It turns out that an infinite number of shrinking steps can still add up to a finite total. Take a 100-meter race. The first step covers 50 meters, the next 25, then 1, 2.5, and so on. Even though this division goes on forever, all those steps still sum up to exactly 100 meters. More importantly, as the distances shrink, so does the time needed to cross them. The total time to reach the finish line stays finite, proving that movement isn't just possible, it happens all around us. Mathematicians use the concept of limits to show that even with an infinite sequence of smaller and smaller steps, motion continues smoothly and naturally. This principle helped pave the way for calculus, the mathematical tool that explains how things move and change over time. But Zeno's paradox isn't just an ancient curiosity, it connects to modern physics in surprising ways. Some scientists believe that space and time might not actually be infinitely divisible. What if, at the tiniest level, movement happens in jumps rather than as a smooth flow? Quantum mechanics suggests that reality might operate in discrete units, much like individual frames in a video. If that's true, then Zeno's paradox might not be as far-fetched as it seems. So, was Zeno just playing mind games, or was he onto something deeper? His paradox challenges us to think critically about motion, space and time, things we take for granted every day. It's a reminder that even the simplest actions like taking a step forward can lead to some of the biggest questions about the nature of reality. Zeno's motion and space paradoxes, Achilles, and the tortoise. Imagine a world-class sprinter, let's say Usain Bolt, lined up against a slow-moving tortoise. Now, to make it fair, the tortoise gets a head start. The race begins, and Bolt explodes off the line. With his incredible speed, it should take him no time at all to overtake the tortoise, right? But according to Zeno, he never actually catches up, ever. Sound ridiculous? That's exactly what the Achilles and the tortoise paradox claims. Let's see how this mind-bending puzzle works. Achilles, the mighty warrior, is the fastest man alive. The tortoise, well, isn't. But to give the tortoise a chance, we let it start 100 meters ahead. Achilles takes off, quickly reaching the tortoise's starting position, but by the time he gets there, the tortoise has moved a little farther. No problem, Achilles runs to that new spot, only to find the tortoise has moved again. Every time Achilles reaches the tortoise's last position, the tortoise is still ahead, just by a smaller and smaller margin. Since this process repeats forever, Zeno argues that Achilles can never truly overtake the tortoise, but wait, something feels off, doesn't it? We see faster runners overtake slower ones every day. We know Achilles should pass the tortoise easily. So where's the flaw in Zeno's logic? The trick lies in how we think about infinity. Zeno treats this chase like an endless series of tiny steps, assuming that because there are infinite steps to take, Achilles needs an infinite amount of time to complete them. But that's not quite right. Imagine pouring a drink into a glass, but each time you pour, you add only half of what's left. You could keep doing this forever in theory, but in reality, the glass does fill up. That's because even though you're dividing the action into infinite parts, the total sum still reaches a limit. Mathematically, this is explained using a concept called a convergent series, where an infinite number of shrinking steps can still add up to a finite number. In Achilles' case, the time it takes for him to close the gap keeps getting shorter and shorter. When we add up all those tiny fractions of time, they form a total that is finite, meaning he does overtake the tortoise, and pretty quickly too. But Zeno's paradox wasn't just about tricking people, it raised deep questions about space, time and movement. Is reality continuous, like a smooth river flowing, or is it made up of tiny indivisible pieces, like pixels on a screen? Even modern physics wrestles with this question. In quantum mechanics, some scientists believe space and time might not be infinitely divisible, but instead composed of the smallest possible units, meaning movement might not be as smooth as it seems. So, was Zeno wrong? Or was he onto something bigger? His paradox forces us to rethink motion, infinity, and the way we experience the world. After all, if something as simple as a race between a man and a tortoise can unravel our understanding of reality, what else are we missing? Zeno's motion and space paradoxes, the Dichotomy Paradox. Have you ever walked across a room? Seems simple enough, right? You take a step, another, and before you know it, you're at the door. But what if I told you that, logically speaking, you should never be able to reach it? According to Zeno's Dichotomy Paradox, getting anywhere is actually impossible. Sounds absurd. Let's break it down. Imagine you're heading toward that door. Before you get there, you have to reach the halfway point. No problem. But before you reach halfway, you need to cover half of that distance. And before that, half again. This process goes on forever, splitting the journey into an infinite number of smaller and smaller steps. If there are infinite steps to complete, how can you ever finish them all? Shouldn't you just be stuck in place forever? And yet, here you are walking around just fine. Clearly something's off. But what? Zeno's paradox plays a clever trick on our understanding of infinity. He assumes that since there are infinite steps to take, the total journey must require an infinite amount of time. But here's the catch. Just because something can be divided infinitely doesn't mean it takes forever to complete. Think about filling a glass with water. If you pour half the glass, then half of what remains, then half again, you're technically dividing the action into infinite steps. But does that mean the glass never fills up? Of course not. Eventually it reaches the top. The same logic applies to motion. Let's say you're in a 10-meter race. You run 5 meters, then 2.5 meters, then 1.25 meters, and so on. Even though there are infinite divisions of distance, the total still adds up to 10 meters. More importantly, each step takes less and less time, meaning that the total time needed to complete the journey stays finite. You reach the finish line just fine. This is where modern mathematics clears up the paradox. In calculus, there's a concept called a convergent series, which shows that an infinite sequence of smaller and smaller numbers can still add up to a finite total. Even though there are infinite steps, the sum of those steps is a real reachable number. That's why you don't get stuck in place every time you try to move. But Zeno wasn't just playing with logic, He was forcing us to think deeply about the nature of space, time, and motion. Are distance and time smooth, continuous flows, or are they made up of tiny, indivisible parts? Even today in quantum physics, scientists are asking whether space and time come in the smallest possible units. If the universe is truly made up of discrete pieces, does that mean Zeno was onto something? So, was Zeno wrong, or was he just ahead of his time? His paradox reminds us that things we take for granted, like simply walking across a room, can unravel into some of the biggest questions about reality itself.
Zeno's motion and space paradoxes. The arrow paradox. Picture this: an archer pulls back the string, eyes locked on the target. The arrow is released, slicing through the air at incredible speed. But wait, what if I told you that, according to Zeno, that arrow isn't actually moving at all? That no matter how fast it looks, it's frozen in place? Sounds impossible, right? But that's exactly what the arrow paradox claims. How can that be? Let's break it down. Imagine time as a series of frozen moments, like frames in a movie. At any single instant, the arrow is in a fixed position, not moving forward or backward. If we analyze every moment separately, we never actually see motion happening. We only see a sequence of still images. If time is just a collection of these frozen moments, how does movement ever occur? But here's the problem. We clearly do see things moving. We see arrows fly, cars speed past, and people walk down the street. So, what's the flaw in Zeno's logic? The mistake comes from thinking of time as nothing more than a collection of still frames. Yes, if you freeze time into individual snapshots, motion seems to disappear. But real motion isn't something that happens inside a single instant, it happens through time. Think of a movie reel. Each frame is a still image, just like in Zeno's paradox. If you pause the film, nothing moves. But when the frames are played in rapid succession, movement appears fluid and natural. Zeno's paradox treats motion like a series of frozen images, forgetting that what matters is how these images connect. Modern physics and mathematics clear this up. Motion isn't something that happens at a single moment, it's something that happens between moments. Imagine driving a car at 60 miles per hour. At any given second, the speedometer still reads 60. Even if we look at just one frozen moment in time, the car isn't stopping and starting in each moment, it's continuously moving. This idea is captured in calculus, where we define velocity as the rate of change of position over time. Even at a single instant, we can calculate how fast something is moving by looking at how its position changes over time. That's why we don't actually see arrows floating motionless in mid-air. But here's where things get really interesting. Zeno's paradox actually raises deeper questions about the nature of time itself. Is time continuous, flowing smoothly, like a river, or is it made up of tiny indivisible moments, like pixels on a screen? In quantum mechanics, some theories suggest that time might not be infinitely smooth, that it could be made up of the smallest possible units, almost like frames in a cosmic film reel. If that's true, then maybe Zeno was onto something all along. So, was Zeno wrong, or did he uncover something deeper about the universe? His paradox forces us to rethink what we take for granted. Something as simple as an arrow flying through the air can lead to some of the biggest questions about space, time, and reality itself.
Zermelos Paradox, the set that shouldn't exist. Imagine trying to collect every possible thing into one giant box. Not just apples or books, but everything, numbers, shapes, even the box itself. Seems reasonable, right? Now what if I told you that, mathematically speaking, this idea doesn't work? Welcome to Zermelos Paradox, a contradiction that emerges when we try to define a set of all sets. It's a concept that sounds simple but collapses under its own weight, much like a snake eating its own tail. Mathematicians love defining collections of objects, which we call sets. You've probably done this without even thinking about it, like saying, all the students in my class or all the books on my shelf. But here's where things get tricky. What happens if we try to define the biggest possible set, one that contains everything? If we call this the universal set, then it should contain every set, including itself. But that's where the problem starts. Think about it. If this set really contains all possible sets, it should also include something called its power set, which is the collection of all the ways we can group its elements. It's like saying, if I have a deck of cards, I can list every possible way to hold some of them in my hand. The strange part, there are always more ways to group things than there are things themselves. This is where Cantor's theorem throws a wrench into our idea of a universal set. It proves that the power set of any collection is always strictly larger than the original collection itself. So, if our universal set contains everything, it must also contain this larger collection, but that's impossible. How can the largest set be smaller than something inside it? That's the paradox. So, how do mathematicians deal with this? Simple, they throw out the idea of a universal set. Modern set theory, specifically Zermelo-Fraenkel set theory, prevents this contradiction by carefully defining how sets can be built. Instead of allowing a set of all sets, it introduces the concept of proper classes, collections that can be described but aren't allowed to behave like normal sets. In short, it tells us some things are just too big to be called a set. Why does any of this matter? Well, this paradox forces us to rethink what everything really means, both in mathematics and beyond. It has deep implications in computer science, where databases and logic systems rely on strict definitions to avoid contradictions. It influences philosophy, raising questions about whether we can ever fully describe reality, and even in physics, theories about the universe often bump up against the limits of mathematical logic. Zermelos Paradox is a perfect example of how infinity plays tricks on us. At first, the idea of a universal set sounds obvious, like something we should be able to construct without issue, but the moment we try, it collapses in on itself. Some infinities, it turns out, are just too infinite to exist.
Richard's paradox. When language becomes a trap. Have you ever tried to describe something so precisely that you end up contradicting yourself? What if I told you that language itself can create a paradox? One that traps us in a loop of logic that seems impossible to escape. This is Richard's paradox, a mind-bending twist in mathematics that exposes the hidden dangers of trying to define everything with words. Numbers are everywhere. We define them all the time without even thinking about it. If I ask you to name the smallest even number, you'd immediately say 2. If I ask for the number of planets in our solar system, you'd probably say 8. Unless Pluto is making a comeback. We do this so naturally that it's easy to assume every number can be named or described in some way. Now, imagine we made a giant list of every number that can be defined in a sentence of 20 words or fewer. Seems like a reasonable thing to do, right? English has a finite number of words, so there must be a limited number of ways to define numbers within that constraint. This means that our list would be countable, meaning we could, in theory, organize it like a phone book and go through it one by one. But here's where things take a weird turn. What about the numbers that aren't on the list? We know that most real numbers, like the ones on the number line between 0 and 1, can't be neatly described in a finite way. So let's try to define a number that isn't on our list, the smallest positive number that cannot be defined in fewer than 20 words. Seems like a good definition, right? But wait, how many words are in that sentence? 14. We just defined something that was supposed to be undefinable in fewer than 20 words. That's a paradox. If this number really couldn't be defined in fewer than 20 words, then we shouldn't be able to describe it with this short sentence, but we just did. On the other hand, if it really has been defined in fewer than 20 words,
then our original statement is false, and the number must have been on the list all along. This logical contradiction creates a loop, one that proves that language, when dealing with infinity, isn't as reliable as we think. This paradox is similar to other mind-bending logical traps, like Russell's paradox, which questions whether a set can contain itself, or the classic liar paradox, where a person says, "I am lying," creating a sentence that can never be true or false at the same time. In all these cases, the contradiction arises because of self-reference definitions that point back to themselves in a way that breaks logic. So why should we care about this? Richard's paradox isn't just some abstract brain teaser, it has real consequences in set theory, logic, and even artificial intelligence. In formal mathematics, it helped shape Gödel's incompleteness theorems, which prove that some mathematical truths can never be formally proven. In computer science, it relates to computability theory, showing that some problems are fundamentally unsolvable, and in philosophy, it challenges the very idea of whether language can ever fully capture reality. It turns out that language, while powerful, isn't perfect. When we try to define the undefinable, we create contradictions that expose the limits of human reasoning. Richard's paradox is a warning: not everything can be neatly boxed into words, and sometimes, the more we try to define something, the more we reveal our own logical blind spots. And so, the question remains, how much of reality is slipping through the cracks of language, right before our eyes?
Hilbert's hotel paradox, checking into the strangest hotel in the universe. Imagine walking into a grand hotel with an infinite number of rooms. It stretches beyond the horizon, never ending. A hotel so vast that it should never run out of space. But here's the catch. Every single room is already occupied. No vacancies, not one. So, what happens when a new guest arrives? You'd expect the receptionist to turn them away, right? Well, not in Hilbert's hotel, where infinity plays by different rules. This thought experiment, proposed by the mathematician David Hilbert, isn't just a quirky brain teaser. It's a window into the bizarre nature of infinity. Picture yourself as the newcomer at this strange hotel. Every room is full, yet the receptionist smiles and says, "No problem, we'll make space for you." How? By shifting every current guest one room up. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. The guest in room 3 moves to room 4, and so on, infinitely. Now, room 1 is empty, and you check in. A full hotel just made space without kicking anyone out. This is how infinity bends our intuition. It's full, but not in the way we expect. Now, an infinite tour bus arrives. One new guest was easy to accommodate, but what if an infinite number of new guests arrives? An endless tour bus rolls up, each seat filled with a new traveler, hoping to stay the night. Surely now the hotel is out of luck. Not at all. The receptionist grins and says, "We'll make space." Here's the trick. Every guest currently in the hotel moves to double their room number. The guest in room 1 moves to room 2, the guest in room 2 moves to room 4, the guest in room 3 moves to room 6, the guest in room 4 moves to room 8, and so on. Now, all the odd-numbered rooms 1, 3, 5, 7 are empty, leaving infinite space for all the new guests. The hotel was full before, and it's still full now, but somehow it fit even more guests. Infinity refuses to behave like normal numbers. What if an infinite fleet of buses arrives? Alright, what if things get really ridiculous? Imagine an infinite number of buses, each carrying an infinite number of guests. Now, there must be no way to make room, right? Think again. The receptionist, never breaking a sweat, has a strategy. Each current guest is assigned a room using powers of the prime number 2. The original guests move into rooms 2, 4, 8, 16, all powers of 2. Now, for the infinite buses arriving,
The first bus's guests take rooms assigned using powers of 3, like 3, 9, 27. The second bus's guests take rooms using powers of 5, like 5, 25, 125. The third bus's guests use powers of 7, like 7, 49, 343. Since prime numbers never overlap, this method ensures every single new guest has a unique room, and the hotel still isn't full. Infinity just doesn't make sense in the way we expect. What does this teach us? Hilbert's hotel challenges everything we assume about infinity. It shows that infinity isn't like finite numbers. A full, infinite set can still have room for more. Some infinities are the same size. The infinity of natural numbers is the same as the infinity of even numbers, odd numbers, or multiples. Even though one seems larger, infinity can be manipulated. We can rearrange infinite sets in surprising ways without changing their total size. Why does this matter? Hilbert's hotel isn't just a thought experiment. It has real-world applications, mathematics, and set theory. It helps explain different sizes of infinity, which influence everything from number theory to calculus, computer science. It relates to infinite loops, memory allocation, and data processing in computing, physics, and cosmology. The universe might be infinite. Understanding infinities is key to understanding space and time. Hilbert's hotel forces us to rethink what it means for something to be full, empty, or larger than something else. It's a paradox that bends logic, revealing just how strange and flexible infinity really is. So the next time someone tells you something is full, just ask them, is it full, or Hilbert's hotel full?
Cantor's paradox, when infinity outsmarts itself. What if I told you that no matter how big you imagine infinity to be, there's always something bigger hiding within it? It sounds impossible, right? But that's exactly what Cantor's paradox reveals, a contradiction lurking in the idea of the largest infinity. It's a puzzle so strange that it forced mathematicians to rethink the very foundations of set theory. Infinity is weird. We think of it as something endless, something ultimate, but mathematician George Cantor discovered something shocking. Not all infinities are the same size. That's right. There are different levels of infinity. Some are bigger than others. Some are so big that they defy logic itself. Let's start with a simple example. Imagine counting 1, 2, 3, and so on. These numbers go on forever, forming an infinite set. That sounds as big as it gets, right? But then, Cantor asked, what about the numbers in between, decimals, fractions, numbers like pi? It turns out, there are infinitely more of those than there are whole numbers. That's right, the infinity of real numbers is bigger than the infinity of counting numbers. It's like realizing there's an even bigger ocean hiding inside an already infinite ocean. But here's where things break down. If some infinities are bigger than others, what happens if we try to collect everything into one ultimate, all-encompassing set? Let's call this the universal set, a set that contains every set, including all possible infinities. Seems logical, right? Now comes the problem. Cantor proved that if you take any set, no matter how large, you can always create a bigger set by listing all its possible subgroups. Think of it like organizing a party. If you have a guest list, you can always make a list of every possible combination of guests, duos, trios, or even just one person by themselves. And strangely, this list of combinations will always be bigger than the original guest list. Now, apply that to infinity. If the universal set truly contains everything, then it must also contain this larger set of all possible subgroups. But Cantor's theorem says that this larger set must be strictly bigger than the original. So now, we have a paradox. How can the biggest possible infinity still be too small to contain something that should be inside it? This contradiction was so mind-blowing that modern mathematics had to make a choice, either abandon logic altogether or change the rules. The solution? We banned the universal set.
mathematicians introduce something called Zermelo-Fraenkel's set theory, which simply does not allow a set to contain everything. Instead, we use the idea of a proper class, a collection that's too big to be treated as a normal set. This avoids the paradox by making sure that no set is allowed to misbehave this way. But why should we care? Well, Cantor's paradox isn't just an abstract curiosity, it has real consequences in computer science, logic, and even philosophy. It tells us that some things are fundamentally beyond comprehension, that some infinities can never be fully contained. It reminds us that even the most basic ideas, like counting, can lead to mysteries that seem impossible to resolve. Infinity, it turns out, is a trickster. No matter how big you think it is, it always finds a way to be bigger.
Banach-Tarski Paradox. The magic trick. That's actually, but if I told you that you could take a single basketball, break it apart, and somehow end up with two identical basketballs without stretching, shrinking, or adding anything. Sounds like a scam, right? But according to the Banach-Tarski Paradox, this isn't a magician's trick, it's real mathematics, and it's about to mess with your perception of reality. This mind-bending result was discovered in 1924 by Stefan Banach and Alfred Tarski, two mathematicians who dared to ask what happens when infinity gets involved in geometry. The answer: the laws of logic start behaving in ways that shouldn't be possible. So, how do you double a ball? Imagine cutting a cake. You can slice it into pieces, rearrange them, but no matter what you do, you still have the same cake, just cut differently. But Banach and Tarski discovered that if you slice something in an infinitely complicated way, you can rearrange the pieces and get double the amount you started with. Mathematically, it checks out. Physically, completely impossible. But why? Breaking reality with the axiom of choice. The trick behind this paradox comes from a mathematical principle called the axiom of choice, which is like a secret cheat code for infinity. It lets you take an infinite collection of things and pick specific elements, even if there's no clear way to do it. Sounds harmless, right? Until it allows you to create extra matter out of nowhere. Here's why Banach-Tarski works. The pieces aren't normal. You're not cutting the ball into simple slices. The pieces you're creating are so infinitely intricate that they don't even have a well-defined size. These are called non-measurable sets, objects that mathematically exist but make absolutely no sense in the real world. No stretching, no shrinking, just rotating. Normally, if you break something apart and put it back together, it still takes up the same amount of space. But here, the pieces are rotated and shifted without stretching or shrinking, and somehow they form two full spheres. Infinity is just that weird. In infinite sets, a part can be just as big as the whole. It's like Hilbert's hotel, where an infinitely full hotel can still fit more guests. Banach-Tarski takes this loophole and uses it to double an entire object. So why can't we do this in real life? If this were possible outside of math, we'd be able to take a single gold coin, slice it up, and rearrange the pieces into two gold coins. Infinite wealth, anyone. So why doesn't this actually work? Reality is built on atoms, not infinity. The Banach-Tarski paradox only applies to a perfectly continuous mathematical sphere, not real objects made of particles. You can't physically cut something infinitely. The pieces required are so bizarre and abstract that even if we had the world's sharpest blade, we couldn't separate them. Physics won't allow it. The laws of quantum mechanics and relativity enforce strict rules about matter and space. If you tried this with actual objects, the universe would simply say, nope. Why does this paradox matter? Even though we can't use it to double our money, Banach-Tarski changes the way we think about reality. Mathematics isn't always intuitive. Some things that make perfect sense in math will never happen in the physical world. Infinity is stranger than fiction.
The way infinite sets behave completely shatters our everyday logic about size, volume, and space. It challenges our trust in math. If math says something can happen, but physics says it can't, what does that mean for how we understand the universe? Infinity, once again, refuses to follow the rules we expect. It doesn't just stretch our understanding, it breaks it in half and doubles it. So next time you hold a basketball, just remember somewhere in the right mathematical framework, that single ball could become two. No magic, no illusions, just pure paradoxical logic.
Boy or girl paradox. The probability puzzle that tricks your brain. Imagine you meet a stranger who casually tells you, "I have 2 kids, and at least one of them is a boy." Now here's a question for you. What's the chance that both kids are boys? You might instinctively say 50%, but hold on. This is where probability plays tricks on intuition. Now let's say the stranger changes the wording slightly. "My older child is a boy." That seems like a small change, right? But guess what? That shift in phrasing completely changes the probability. How? Let's break it down. To figure out the odds in the first version, where at least one child is a boy, we need to list out all the possible ways a 2-child family can exist. Since each child has an equal chance of being a boy or a girl, the possibilities are boy, and boy, boy, and girl, girl, and boy, girl, and girl. Now we were told at least one child is a boy, so we can eliminate the girl and girl option. That leaves us with 3 remaining possibilities: boy, 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 girl, and girl, boy. Only one of those 3 is boy, boy. So the probability that both children are boys is actually 1 out of 3, or roughly 33%. But now, let's switch to the second version, where we are told the older child is a boy. That means we don't need to consider all 4 possibilities, just the 2 where the first child is already a boy. That leaves us with boy, and boy, boy, and girl. Now the only question is whether the younger child is a boy or a girl. Since both are equally likely, the chance of having 2 boys is now 1 out of 2, or 50%. Wait, how did we go from 33% to 50% just by changing the way the question was framed? That's what makes this a paradox. The difference comes down to whether we're talking about at least one child being a boy, which keeps more possibilities open, versus a specific child being a boy, which narrows down the outcomes. It's a great example of how wording completely changes probability, something that actually matters in real life. Think about medical testing. If a doctor tells you that a test is 90% accurate, does that mean you're 90% likely to have the disease if you test positive? Not necessarily. It depends on the overall population and other conditions. Or in AI, where machine learning models constantly make predictions based on partial information, just like this paradox. So the next time someone throws a probability puzzle at you, don't just go with your gut, think about what's actually being asked, because sometimes a tiny change in words can flip the whole answer upside down. Birthday paradox. The surprising odds of shared birthdays. Imagine you walk into a party with a bunch of strangers. As you look around, you think, what are the odds that 2 people here share the same birthday? You probably assume the chances are low. After all, there are 365 days in a year. Surely you need a massive crowd before birthdays start repeating, right? What if I told you that in a room with just 23 people, there's already a greater than 50% chance that at least 2 people share a birthday? And if the room has 57 people, that probability shoots up to over 99%. Sounds impossible, doesn't it? That's the birthday paradox in action. Most people get tripped up because they think about the problem the wrong way. You might be imagining it like this: what's the chance that someone here has my birthday? That's a different question entirely. The real question is, what's the chance that any 2 people
out of all possible pairs, share a birthday. And that changes everything. Picture this. If you're alone in a room, there's obviously no match. Add one person, and there's a tiny chance they share your birthday. Add a third, and now you're checking two different birthday comparisons. A fourth person. Now you have 6 different comparisons happening. The number of possible birthday comparisons grows way faster than you'd expect. By the time there are 23 people in the room, the odds of at least one match are already greater than 50%. It's weird, right? Our brains struggle with probability like this because we tend to focus on individuals rather than groups. But in reality, the number of comparisons skyrockets as more people join in. So why does this matter, outside of party tricks? Well, believe it or not, this paradox is used in cybersecurity. Hackers exploit a similar principle in something called a birthday attack to crack encrypted data. It's also relevant in data science, helping businesses predict duplicate records in huge datasets. Even event planners use it to anticipate how often birthday coincidences will happen at gatherings. It's a fun puzzle, but it teaches an important lesson. Probability often works in ways that completely defy our intuition. So next time you're at a party, try this. Ask how many people are there, then impress everyone by predicting a shared birthday. Just don't forget to check before making a big bet. 2 Envelopes Paradox. The endless game of second-guessing. Imagine someone hands you 2 envelopes. You're told one contains twice as much money as the other. You pick one at random, and before you even open it, you get an offer. Do you want to switch? Sounds like a simple choice, right? But what if I told you that, no matter which envelope you pick, it always seems like switching is the better option? And if that's true, shouldn't you just keep switching forever? That's where the paradox begins. Let's break down the logic that tricks so many people. Suppose your chosen envelope contains some amount of money. Let's just call it X. That means the other envelope must contain either twice as much 2x or half as much x2. Since you don't know which is which, you might think there's an equal chance of either outcome. So if you switch, half the time you'll double your money, and the other half, you'll lose half. When you compare the average of these two possibilities, it seems like switching should always give you a higher expected payout. But wait, this logic applies no matter which envelope you started with. That means you could keep swapping forever, stuck in an endless loop of indecision. That's the paradox. If switching is always the right move, when do you stop? The flaw in this reasoning is subtle but important. The key mistake is assuming that the amounts in the envelopes are chosen in a way that makes switching always beneficial. But in reality, the way the money was placed in the envelopes matters. If there's no predefined rule for how the amounts are chosen, then the entire probability calculation falls apart. So should you switch or not? The truth is, without knowing how the envelopes were filled, there's no real way to determine whether switching is a good idea. The paradox isn't about tricking you into swapping indefinitely. It's about showing how mathematical intuition can break down when probability is misunderstood. But this puzzle isn't just an amusing brain teaser. It actually has real-world implications in fields like gambling and betting strategies. When playing games of chance, recognizing flawed probability assumptions can keep you from making bad bets. Artificial intelligence, AI systems that make decisions under uncertainty, need to be programmed to avoid these logical traps. Game theory and economics, understanding how people make choices based on incomplete information, can lead to better decision-making strategies. So next time someone hands you 2 envelopes and dares you to switch, ask yourself, is this a real opportunity, or just another version of an impossible paradox? The secretary problem, the tricky game of knowing when to stop. Imagine this. You're hiring for a crucial role, maybe a personal assistant, a business partner, or even choosing a place to live. You have a lineup of candidates, each walking in one by one. The catch, you must decide immediately whether to accept or reject each person. and once you pass someone up, they're gone forever. No second chances, no do-overs. How do you make the best possible choice? You might think, well, I should just wait and see as many as possible before choosing. But if you wait too long, you might let the best ones slip away. If you choose too soon, you risk missing someone even better. So what's the smartest approach? Surprisingly, mathematicians have cracked this puzzle. The best strategy is something called the 37% rule. Here's how it works. First, you observe and reject the first 37% of candidates. You don't hire anyone during this phase, just gather information to set a benchmark for what a strong candidate looks like. Then, after this observation period, you hire the very first person who is better than everyone you've seen so far. Simple, right? But why does this work? It turns out this strategy gives you a 37% chance of picking the best candidate, which is shockingly high, compared to choosing randomly. The logic is that by rejecting the first portion, you gain valuable insight into what good looks like, and by acting quickly when you find a standout, you maximize your chances of success. Let's make this more relatable. Ever browsed for an apartment? You visit a few, but don't commit immediately. You need a sense of what's out there. Then, when you find a place that checks all the boxes, you lock it in before someone else takes it, or think about dating. How do you know when to stop searching and commit to someone? The secretary problem suggests that after experiencing about 37% of your expected dating pool, you'll have the best chance of recognizing and choosing the ideal partner. The lesson here: gather information first, but don't hesitate when the right opportunity comes along. Whether you're hiring, dating, or making life-changing decisions, understanding when to stop searching and when to act is key. So next time you're faced with a big choice, remember the secretary problem. You don't always need to see everything, just enough to recognize the best when it appears.
St. Petersburg Paradox. The tempting game of infinite winnings. Imagine someone offers you a simple gamble. You pay to play, and all you have to do is flip a fair coin until it lands on heads. The payout? It doubles every time the coin lands on tails before that first heads appears. Sounds like easy money, right? Let's break it down. If you get heads right away on the first flip, you win $2. If you get tails first and then heads, you win $4. If you get tails twice before landing heads, your prize jumps to $8. Keep flipping tails, and the prize keeps doubling: 16, 32, 64, and so on, growing larger each time. Now, here's the million-dollar question. How much would you be willing to pay to play this game? At first, it seems like this game should be worth a fortune. After all, you could, in theory, keep flipping tails and walk away with an astronomical payout. But here's where it gets weird. When mathematicians calculate the expected value, the answer comes out as infinite. Yes, infinite. On paper, a rational gambler should be willing to pay any amount to play, but in reality, if someone offered you this game, you probably wouldn't pay more than a few bucks to enter. Why? Because real people don't think like equations. One reason is diminishing marginal utility. The idea that the value of money isn't linear. Winning $1,000 feels great, but it doesn't feel 10 times better than winning 100. At some point, more money stops feeling as impactful. That's why most people aren't willing to spend huge amounts on a game where the most extreme payouts are incredibly rare. Then there's the practical side. Who's actually going to pay you $1 billion if you get incredibly lucky? No casino, no gambler, and definitely no game host has infinite money to back up this deal. Even if the expected payout is infinite, the real-world payouts are limited, and let's not forget risk aversion. Sure, the game has an infinite expected value, but most people prefer a guaranteed amount of money over a wildly uncertain bet. The biggest payouts require a ridiculous streak of tails.
something that happens so rarely that it's hard to justify paying too much for the chance. This paradox isn't just some theoretical curiosity, it's influenced economics, insurance, and behavioral psychology. It explains why people don't always act according to pure math, why we buy insurance even when the numbers say we shouldn't, and why the stock market doesn't behave like a perfect machine. So the next time someone offers you a can't-lose deal, ask yourself, is this a St. Petersburg Paradox in disguise? Because sometimes, even when the math says you should go all in, reality has a very different answer.
Sorites Paradox. Paradox of the heap. If you take away just one grain of sand from a heap, it's still a heap, right? And if you remove one more, it's still a heap. But what if you keep going, one grain at a time? At what point does the heap stop being a heap? That's the Sorites Paradox, a puzzle that messes with our sense of logic, showing how small, seemingly insignificant changes can add up to something completely different. And it's not just about sand, it's about language, identity, and the way we define reality. Think about it. When does a person go from being young to old? When does a few dollars become wealth? At what point does hair loss turn someone bald? These concepts don't have clear boundaries, yet we use them every day. So how do we decide where to draw the line? Philosophers have tackled this paradox from different angles. Some say there must be a precise cutoff, even if we don't know where it is. Others argue that vague terms like heap or bald don't need exact definitions, because we understand their meaning in context. Then there's fuzzy logic, which suggests that truth isn't black and white, but exists in degrees. Maybe a pile of sand is 80% heap, rather than an all-or-nothing definition. And this isn't just a fun thought experiment. This paradox pops up everywhere. In law, vague terms like reasonable doubt and fair punishment can be the difference between justice and injustice. In medicine, doctors must decide when a condition crosses the threshold from mild to severe. In AI, computers struggle to process vague human concepts like nearby or warm. Even in politics, shifting labels like middle class or developing nation can change entire policies. So what's the takeaway? The Sorites Paradox reminds us that many of the concepts we rely on are built on arbitrary boundaries, and yet, even without clear-cut definitions, we still navigate the world just fine. Maybe the real lesson isn't about finding the perfect dividing line, it's about recognizing that sometimes a little vagueness is just part of how we make sense of things.
Sleeping Beauty Paradox. The mind-bending game of probability. Imagine you agree to take part in an experiment. On Sunday night, you're put to sleep, and a coin is flipped. You have no idea what the result is, and when you wake up you feel normal, until someone asks you a strange question. What is the probability that the coin landed on heads? Sounds simple, right? A fair coin has a 50% chance of landing on heads, and a 50% chance of landing on tails. But here's the twist. Your memory is being erased after each awakening, and depending on how the coin landed, you might have woken up once or twice without knowing it. Here's how the experiment works. If the coin landed on heads, you're awakened on Monday, ask the question, and then put back to sleep. That's it. If the coin landed on tails, you're awakened on Monday, ask the same question, put back to sleep, with your memory erased, and then awakened again on Tuesday, and ask the same question, once more. So now, when you wake up you have no clue whether it's Monday or Tuesday. All you know is that you're in the middle of the experiment, answering the same question, with no recollection of whether you've been here before. So, what's the correct answer? Is the probability of heads still 50%? Or does the fact that you might have woken up twice on tails change the math? Some say the probability is 1 in 2. That's the alpha. argument. They believe that since the coin was fair, nothing in the experiment should change its original 50/50th chance. To them, the fact that you wake up doesn't give you any new information about the coin flip itself. Others say the probability is 1 in 3. That's the third argument. They argue that when you wake up, there are 3 equally possible ways the experiment could be playing out. It's Monday, and the coin landed on heads. It's Monday, and the coin landed on tails. It's Tuesday, and the coin landed on tails. Since these 3 possibilities are equally likely, but only one of them involves heads, the probability of heads should be 1 in 3, or about 33%. This paradox isn't just a brain teaser, it actually connects to real-world problems in probability, philosophy, and even physics. It mirrors ideas in Bayesian reasoning, where beliefs need to be updated based on new information. It also has parallels in quantum mechanics, where different realities exist until an observation is made, and in artificial intelligence, this kind of problem is crucial for systems that make decisions based on limited or uncertain data. So, what do you think? Do you trust the original 50/50ths odds, or do you believe that waking up in the experiment makes tails twice as likely? The Sleeping Beauty problem has sparked debates for decades, and the best part, there's still no universally accepted answer. Ship of Theseus, the paradox of identity. What makes something the same thing over time? Is it the material it's made of? Or something deeper? Imagine you have an old beloved ship. Over the years, its wooden planks start to rot, so you replace them, one by one, until eventually every single part has been swapped out. Now, here's the big question. Is it still the same ship? Now let's make it even trickier. What if someone took all the old planks, the ones you replaced, and reassembled them into a ship that looks exactly like the original? Now we have 2 ships, one with all new parts, but continuous history, and one made entirely of the original pieces. Which one is the real ship of Theseus? Or, more importantly, does it even matter? This is where things get messy. The Ship of Theseus paradox isn't just about boats, it's about identity, change, and what it really means to be the same thing over time. Some argue that identity comes from physical substance, meaning the ship made from the original wood is the real one. But others say identity comes from continuity, meaning the ship that stayed in the harbor, even though it's been rebuilt, is still the Ship of Theseus. And then there's an even wilder idea. What if identity is just an illusion? Some philosophers suggest that things, including people, don't have a fixed identity at all, just like a river remains the same, even though the water is constantly flowing. But this paradox doesn't just apply to ships, it applies to you. Your body is constantly replacing cells, your memories shift and fade. Are you the same person you were 10 years ago? At what point do you become someone new? Think about technology. If you upgrade every part of a computer over time, is it still the same machine? If we replace parts of the human brain with artificial implants, at what point does someone stop being human? These questions aren't just theoretical, they're real challenges we might face in the future. Even in art and history, we see this paradox in action. If a famous painting is gradually restored with new paint, is it still the same painting? If a historic monument is rebuilt after being destroyed, is it still authentic? So, what's the answer? Maybe there isn't one. Maybe identity isn't about physical parts or history, it's about perception. Things are what we believe them to be. Whether it's a ship, a person, or an idea, identity is something we define, not something that exists on its own. And that might be the most mind-bending part of all. So, what do you think? If everything about you slowly changed over time, at what point would you stop being you?
Paradox of the court, the endless trial of logic. Imagine you're a student, eager to learn the art of persuasion from one of the greatest teachers of the time. You strike a deal, one that seems completely fair. You won't have to pay your teacher
until you win your first case in court. Sounds reasonable, right? But what if that deal creates a legal nightmare with no way out? That's exactly what happened between Protagoras, a brilliant Greek philosopher and teacher, and his student, Euathlus. Euathlus trained under Protagoras, agreeing that payment would only be due if and when he won his first case. But here's where things took a turn. After completing his lessons, Euathlus simply didn't take any cases. No victories, no losses, just silence. And that meant no payment for Protagoras. Protagoras wasn't about to let that slide. If Euathlus refused to go to court voluntarily, Protagoras would drag him there himself. And so, in a strange twist, Protagoras sued Euathlus, leading to one of the most famous legal paradoxes in history. The moment the trial began, it became clear that no matter how the court ruled, a contradiction would arise. Protagoras argued, if the court rules in my favor, then Euathlus must pay me, because that's the court's decision. But if the court rules against me, then Euathlus has won his first case, which means the original agreement requires him to pay me anyway. Either way, I get my money. Euathlus, calm and confident, had a counter-argument ready. If I win this case, then the court has ruled that I don't have to pay you. If I lose, then I still haven't won my first case, so by our original deal, I don't have to pay you yet. Either way, I don't owe you a thing. See the problem? Both arguments seem airtight, yet they completely contradict each other. No matter what decision the court made, it would prove the opposite argument correct. So, what's the right answer? Who should win? That's the paradox. The case traps itself in an endless legal loop, making it impossible to resolve in a logical way. This puzzle isn't just an ancient curiosity, it reveals something deeper about how we interpret laws, contracts, and logic. Can agreements be absolute, or do they depend on context? Can legal systems handle situations where both sides are technically right? And how often do we face modern dilemmas where the rules contradict themselves? Think about contract loopholes in business deals, or court cases where two sides interpret the same law in completely different ways. Even in everyday life, how often do we find ourselves in situations where right and wrong aren't so easy to define? The paradox of the court has fascinated thinkers for centuries because it exposes the fragility of logical systems when rules clash. Whether it's law, philosophy, or game theory, this paradox reminds us that sometimes even the best arguments can lead to an unsolvable riddle. Paradox of analysis, the dilemma of defining concepts. Have you ever tried to explain something simple, only to realize that defining it makes it seem even more complicated? What if every definition you gave was either too obvious or too misleading? That's the paradox of analysis, a puzzle that forces us to rethink how we define even the most basic concepts. Imagine someone asks, "What does good mean?" You confidently reply, "Good means that which is morally right." Seems reasonable, right? But if that's correct, then you haven't actually said anything new, just swapped one phrase for another. And if your definition does say something new, then it must not be exactly the same as the original meaning. So, which is it? Is a definition correct but useless, or useful but incorrect? It seems like every definition is trapped in this paradox, stuck between being either trivial or wrong. This issue might sound like just a word game, but it's actually a deep problem that affects how we communicate, learn, and even how artificial intelligence processes information. If we can't define concepts without losing meaning, how do we ever expand our knowledge? Some of the greatest philosophers have wrestled with this paradox. G. Moore, who first described it, believed that defining concepts should reveal their exact meaning without changing them, but that led to definitions that felt completely uninformative. C.H. Langford later argued that a definition should explain how a concept functions, not just restate it. Then, there's Ludwig Wittgenstein, who flipped the whole problem on its head. He argued that meaning isn't found in strict definitions, but in how we use words in real life. Instead of trying to capture a concept in one rigid phrase, we should look at how people actually apply it across different situations. This paradox isn't just some abstract philosophical curiosity, it has real-world consequences. Think about law and legislation. Courts struggle with defining terms like reasonable doubt. If the definition is too vague, it's useless. If it's too specific, it might exclude cases where common sense says it should apply. Or take artificial intelligence. If AI systems are programmed with rigid definitions, they might fail to recognize subtle variations in meaning. If the definitions are too broad, the AI might misinterpret information. Even in science, definitions have to balance between precision and usability. A term like energy in physics needs an operational definition, one that scientists can apply in different contexts without making it meaningless. So how do we escape this paradox? Some philosophers suggest that definitions should always be context-dependent, changing based on how they are used. Others argue that instead of searching for one perfect definition, we should layer multiple definitions together to get a fuller picture. Some even take a pragmatic approach, saying we shouldn't obsess over perfect definitions as long as they work in practice. At the end of the day, the paradox of analysis reminds us that language isn't just about matching words to meanings, it's about understanding how we use those words in the real world. Definitions may never be perfect, but that doesn't mean they aren't useful. Instead of looking for absolute answers, maybe the best way forward is to embrace the complexity and adapt our understanding as we go. After all, isn't that what learning is all about?
Newcomb's Paradox, the mind-bending game of prediction. Imagine you're standing in front of two boxes. One is clear, holding a guaranteed $1,000. The other is opaque. You have no idea what's inside. It could be completely empty, or it could contain a staggering $1 million. The choice seems simple, right? Just take both, and walk away with whatever's there. But here's where things get weird. There's a powerful predictor involved. An entity so intelligent, so eerily accurate, that it has never been wrong. It already predicted what you're going to do. If it foresaw that you would take only the opaque box, then it placed $1 million inside. But if it predicted that you'd go for both boxes, it left the opaque one empty. So now, you're faced with a dilemma. Do you take only the opaque box, trusting that the predictor saw this decision coming and left you a fortune? Or do you take both, reasoning that the money inside was already placed and nothing you do now can change that? It's a battle of logic versus trust, and people are split into two camps. The one-boxers argue, if I take only the opaque box, the predictor would have foreseen it and rewarded me with $1 million. If I get greedy and take both, the predictor would have seen that too and left me with just the $1,000. The only smart move is to trust the predictor. The two boxers scoff. Hold on, the money is already inside the opaque box. Before I make my choice, it's either there or it's not. Nothing I do now can change that. Since I know the clear box has 1,000, why not take both? If the opaque box happens to have the $1 million, great. I walk away with a total of $1 million and 1,000. If not, I still get something. And that's why this is a paradox. Both arguments sound completely rational, yet they lead to opposite conclusions. Who's actually right? Some say this paradox forces us to rethink free will. If the predictor is always right, do you really have a choice? Others say it's a test of belief in determinism versus randomness. And in the realm of artificial intelligence, game theory, and even quantum mechanics, this paradox touches on deep questions about how we make decisions. So, what would you do? Trust the predictor and take only the opaque box, or go for both, knowing that whatever's inside is already decided? It's a choice between logic and faith, and no matter which side you take, the paradox wins.
Moore's paradox, the problem of belief and assertion. Have you ever said something and immediately felt like it didn't quite make sense, even though the words were correct? Imagine saying, "It is raining, but I don't believe that it is raining." Sounds strange, right? It's not a grammatical error, and it's not a contradiction in formal logic, but something about it just feels off. That unsettling feeling is the heart of Moore's paradox, a philosophical puzzle first introduced by G.E. Moore in the early 20th century. It forces us to question the way we understand belief, assertion, and rational thought. Why does saying something, while simultaneously denying belief in it, create such an odd conflict? And what does it tell us about how our minds work? Picture this. You tell your friend, "I have a headache, but I don't believe I have a headache." What would they think? Probably that you're confused, joking, or maybe even losing touch with reality. The same goes for saying, "The Earth orbits the Sun, but I don't believe that the Earth orbits the Sun." Even if both parts of the sentence are true, putting them together feels irrational, like your own beliefs are disconnected from reality. So why does asserting something imply that you believe it? If beliefs and statements are separate things, shouldn't it be possible to say something is true while not personally believing it? Moore's paradox suggests there's an unspoken rule in communication. If you assert something, you must also believe it to be true. Otherwise, why would you say it? Philosophers and logicians have debated this paradox for decades. Moore himself argued that while sentences like "it is raining, but I don't believe it" are not logically contradictory, they are epistemically contradictory, meaning they create a clash between what we claim to know and what we claim to believe. Ludwig Wittgenstein took this further, suggesting that saying something implies belief in it, because that's how language naturally works. It's not a rule of logic, it's a rule of how humans communicate. But is this just a quirk of language, or does it reveal something deeper about how our minds process belief? Some psychologists see Moore's paradox as a form of cognitive dissonance, the mental discomfort that happens when we hold conflicting thoughts. Think about someone who says, "I know smoking is bad, but I don't believe it will harm me." That contradiction exists in everyday life, not just in philosophy books. This paradox even appears in mental health. A person with depression might say, "I know people love me, but I don't believe they do." They recognize the truth logically, but they cannot fully accept it on a personal level. This kind of disconnect is a real-world version of Moore's paradox in action. Even artificial intelligence struggles with this problem. AI systems rely on logical consistency, but what happens when they encounter contradictions between data-driven truth and human belief systems? If a machine learning model knows something but can't believe it, can it still function rationally? The paradox highlights key challenges in designing AI that mimics human reasoning. In legal cases, similar contradictions arise all the time. A defendant might say, "I signed the contract, but I don't believe I agreed to its terms." The words make sense individually, but together they create confusion about intent and responsibility. So, is there a way out of the paradox? Philosophers have suggested a few possible solutions, redefining assertion and belief. Some argue that asserting something should always imply belief, making Moore's paradox a violation of communication norms rather than a logical contradiction. Refining the concept of belief, others propose that belief should include an awareness component, meaning, if you believe something, you must also recognize that you believe it. Treating it as a psychological illusion, maybe the paradox is simply an illusion caused by how human minds process language and thought. We assume that assertion implies belief, but perhaps that's not an absolute rule. No single answer fully resolves Moore's paradox, but it does challenge us to think about the connection between what we say and what we actually believe. It forces us to confront the gap between knowledge and self-awareness, and maybe, just maybe, it reminds us that human thinking isn't always as logical as we'd like to believe.
Monty Paradox, the mind-bending game of switching choices.
Imagine you're on a game show. The bright stage lights are on you. The audience is holding its breath, and you're staring at 3 closed doors. Behind one of them, a brand new car. Behind the other 2, goats. You make your choice and pick a door. Just as your heart starts racing, the host, who knows exactly where the car is, steps in. With a smile, he opens one of the remaining doors, revealing a goat. Now, he turns to you and asks, do you want to stick with your original choice, or switch to the other unopened door? Your instincts tell you, it doesn't matter, there are 2 doors left, so it's a 50-50th chance now, right? But what if I told you that's completely wrong, that the best choice every single time is to switch? Here's why. When you first pick a door, your chances of picking the car are only 1 in 3. That means there's a 2 out of 3 chance that the car is behind one of the doors you didn't pick. The host, who always knows where the car is, then eliminates one of those losing doors, leaving you with a choice: stay with your original 1 in 3 pick, or switch to the other door, which now holds the full 2/3 probability of being right. Let's break it down another way. Imagine playing this game 100 times. If you always stuck with your first choice, you'd win only about 33 times. But if you always switched, you'd win nearly 67 times. That's double the number of wins, just by making the counterintuitive choice to switch. And yet, people still refuse to believe this. Even mathematicians have gotten it wrong at first glance. Why? Because our brains hate counterintuitive probabilities. We want to believe that when 2 options remain, they must be equally likely. But they're not. Because the host's decision to open a door isn't random, it's giving you information. This isn't just a game show trick. The Monty Hall problem actually plays out in real life all the time. Medical testing. If a disease is rare, how should a doctor adjust their confidence in a positive test result? AI and machine learning. How can a computer update its predictions when new data comes in? Everyday decisions. When you learn new information about a choice, do you stick to your gut or adjust based on probabilities? So the next time you face a choice that seems like a 50-50th toss-up, stop and ask yourself, is this a Monty Hall moment? Because if it is, your instincts might be steering you the wrong way, and just like on that game show stage, the difference between sticking or switching could be the difference between a goat and a brand new car. Hedgehog's dilemma. The paradox of intimacy. Have you ever wanted to get close to someone but hesitated, afraid of getting hurt? Maybe in a friendship, a relationship, or even with family. It's that tricky balance, wanting warmth and connection, but fearing the pain that sometimes comes with it. That struggle is at the heart of the hedgehog's dilemma, a paradox that reveals just how complicated human relationships really are. Picture this: it's a freezing winter night, and a group of hedgehogs huddle together for warmth. But as they inch closer, their sharp spines prick one another. The pain forces them to move apart, but then they're cold again. So, what do? How close can they get before the pain outweighs the warmth? Now, swap out the hedgehogs for humans. The paradox is no longer about sharp spines, it's about emotional vulnerability. People crave connection, but getting close to others means exposing themselves to potential hurt, whether through misunderstandings, rejection, or betrayal. So, how do we navigate relationships without pulling away completely? Some philosophers have some pretty bleak answers. Arthur Schopenhauer, who first introduced this idea, believed that human relationships are doomed to be painful because people can never truly escape emotional suffering. His advice? Keep your distance, stay detached. Not exactly comforting, right? Sigmund Freud later picked up on this dilemma, linking it to his theories of human attachment. He argued that relationships are a constant battle between the need for closeness and the instinct for self-preservation. In modern psychology, this idea aligns with attachment theory, which explains why some people seek deep emotional intimacy, while others push it away to protect themselves. Ever known someone who's terrified of commitment, or someone who clings too tightly. They might just be playing out their own version of the hedgehog's dilemma, and it doesn't just apply to romance. Think about friendships. Have you ever hesitated to open up to someone because you were afraid they might not understand? Or what about family? Parents and children crave closeness, but miscommunication can drive them apart. Even in the workplace, too much emotional involvement can lead to conflict, while too much distance creates isolation. The dilemma is everywhere. So, what do we do? Do we resign ourselves to a life of isolation, or do we throw caution to the wind and risk getting hurt? The good news is that unlike hedgehogs, we have more tools at our disposal. Healthy boundaries allow us to enjoy connection without sacrificing emotional safety. Communication and emotional intelligence help us express our needs without hurting others. Mutual understanding lets us respect different comfort levels in relationships, and most importantly, trust takes time. Building intimacy gradually makes it easier to navigate the risks that come with closeness. The hedgehog's dilemma isn't about avoiding connection, it's about finding the right balance. Just like those little creatures on a winter night, we're all trying to get close without causing unnecessary pain, and maybe, just maybe, if we take the time to understand ourselves and each other, we can find that perfect distance where warmth and safety coexist.
Census taker paradox. The mysterious case of missing information. Imagine a knock at the door. You open it to find a census taker standing there, clipboard in hand. How many children do you have? And what are their ages? They ask. Seems like a simple question, right? But what if the answer led to a puzzle so tricky it left even a trained census worker scratching their head? The man at the door replies, I have 3 children, and if you multiply their ages together, you get 36. The census taker jots this down, but frowns. That alone isn't enough information. Can you give me another clue? The man nods and adds, the sum of their ages is the same as my house number. The census taker checks the number on the house and thinks for a moment, but something is still off. I still can't figure it out. Is there anything else you can tell me? The man smiles and says, my oldest child plays the piano. In an instant, the census taker's face lights up. Now I know their ages. Wait, what just happened? How did that last clue suddenly make everything clear? To solve the puzzle, let's break it down. The first clue tells us that when you multiply the 3 ages together, the result is 36. There are several possible sets of ages that could fit: 1, 1, and 36, 1, 2, and 18, 1, 3, and 12, 1, 4, and 9, 2, 3, and 6, 1, 6, and 6, 2, 2, and 9. Still confused? So was the census taker. That's why the second clue was needed. The sum of the 3 ages matches the house number. Normally that would give away the answer immediately. But here's the trick. There must have been 2 sets of ages that added up to the same number. That's why the census taker was still uncertain. And sure enough, there are exactly 2 sets that both add up to 13. 1, 6, and 6, 2, 2, and 9. Now the final clue comes into play. My oldest child plays the piano. That means there has to be a single oldest child. But in the first set, 1, 6, and 6, there is no single oldest child. The 2 6-year-olds are the same age. However, in the second set, 2, 2, and 9, there is a clear oldest child, the 9-year-old, and that's how the puzzle is solved. The man's children must be 2, 2, and 9 years old. Why does this paradox stand out? It plays with the idea that we often assume we have enough information to solve a problem, when, in reality, we might be missing one crucial piece. It's a lesson in logical thinking, problem solving, and knowing when to look beyond the obvious. This kind of logical deduction isn't just for brain teasers. It's used in artificial intelligence,
detective work, and even medical diagnoses. The ability to recognize missing information and use indirect clues to find an answer is a skill that applies everywhere. So the next time you think you've got all the information you need, ask yourself, am I missing the final clue?
Buridan's ass. The paradox of rational choice. Have you ever been stuck between two choices, completely unable to decide? Maybe staring at two equally good menu options, flipping between two job offers, or just trying to pick a movie? What if I told you that this kind of indecision, if taken to the extreme, could actually lead to disaster? Welcome to Buridan's ass, a paradox that shows just how dangerous overthinking can be. Imagine a donkey. Let's call him Bob. Bob is both hungry and thirsty. Luckily, he finds himself standing exactly halfway between a pile of hay and a bucket of water. Perfect, right? Well, not quite. Bob is a purely logical creature, and since the hay and the water are equally desirable and equally distant, he has no rational reason to choose one over the other. So what does Bob do? Nothing. He stands there, unable to make a decision, until he starves and dies. Sounds ridiculous, maybe. But before you laugh at Bob, think about how often we freeze up in decision-making. Ever spent way too long picking a show on Netflix, only to end up watching nothing? Ever debated a purchase for so long that the sale ended, and you got nothing at all? Bob's dilemma might not be as far-fetched as it seems. The real question is, can we be too rational? If we always demand a perfect reason to choose one thing over another, what happens when no perfect reason exists? Are we just as stuck as Bob? Philosophers have spent centuries debating this paradox. Some argue it challenges determinism, the idea that all decisions are caused by prior reasons. If every action is determined by logic, then what happens when logic offers no solution? Does this mean free will or even randomness must play a role in our choices? Others apply it to decision theory, pointing out that in reality, people rarely get completely stuck like Bob. We use emotions, instincts, and even random impulses to break the tie when logic fails us. Even when faced with two equally good options, we might choose based on habit, a small preference, or just gut feeling, things Bob, being a purely rational donkey, doesn't have. And this paradox isn't just some abstract thought experiment, it plays out in real life all the time. AI and algorithms, for example, sometimes run into a Buridan's ass situation. If a program is designed to make decisions based on equal weighted factors, it can freeze, unable to prioritize one option over another. That's why programmers often introduce randomization or slight biases to keep systems from getting stuck. Even business and economics face this issue. Imagine two equally promising investments. If a company waits too long to decide which one to pursue, they might miss both opportunities. In psychology, we see this play out in decision fatigue. When people are overwhelmed by too many options, they sometimes end up making no decision at all. So how do we escape the paradox? Simple, just choose something. Even if two options are truly equal, we can break the tie in several ways. Flip a coin. Random choice is still a choice. Trust your gut. Even a tiny unconscious preference can be enough. Set a deadline. Giving yourself a time limit forces action. Ask for advice. Sometimes an outside perspective makes the decision easier. Buridan's ass isn't just about a donkey, it's about the dangers of overthinking. Waiting for the perfect reason to act can sometimes mean never acting at all. Whether it's in philosophy, business, or everyday life, the lesson is clear. Indecision can be more dangerous than making the wrong choice. So next time you find yourself stuck, remember Bob, and for your own sake, don't be a donkey. Ellsberg Paradox. Why we fear the unknown. Imagine you're about to make a simple bet. In front of you is a large urn filled with 90 balls. You know that 30 of them are red, but the remaining 60 could be either black or yellow in any proportion. You have no idea how they're split. Now you have two choices. Bet on red being drawn. Bet on black being drawn.
which one do you pick? Most people choose red. It feels safer because you know exactly how many are in the urn. But now, let's change the game. You're given two new options. Bet on black or yellow being drawn. Bet on red or yellow being drawn. Now, most people switch and pick black or yellow. But wait, didn't you just avoid betting on black before? What changed? Nothing. Yet people's choices contradict each other. This is the Ellsberg Paradox, and it exposes a flaw in how we handle uncertainty. People would rather pick a known risk than face the unknown. Our brains are wired to avoid ambiguity, even when it means making inconsistent choices. We prefer bets where the odds are clear, even if the actual probability of winning is the same in both scenarios. It's not that red was a better choice, it just felt less uncertain. This fear of the unknown impacts real-world decisions more than you'd think. Investors hesitate to put money into new, unfamiliar markets, even if they have the same expected returns as well-known ones. Businesses avoid risks that lack clear data, even when they might have the best potential rewards. Politicians make policies based on what they know, rather than what might be better, but is less understood. But here's the thing, sometimes, the best opportunities lie in the unknown. The companies that disrupt industries, the investors who make bold moves, and the leaders who change the game are the ones who don't let ambiguity hold them back. So how do you beat the Ellsberg Paradox? First, recognize when fear of uncertainty is affecting your decision-making. Second, focus on actual probabilities rather than gut feelings about ambiguity. And finally, remember that avoiding risk doesn't always mean making the smartest choice. The next time you hesitate because something feels too uncertain, ask yourself, are you really making the best decision, or are you just avoiding the unknown? Gambler's fallacy. When your brain tricks you at the casino, you're sitting at a roulette table, watching the wheel spin. The last 5 spins have all landed on red. Your heart starts racing. There's no way it can land on red again, right? It feels like black has to come up next, so you push all your chips in, convinced the pattern is about to change, and then, red, again. This is the gambler's fallacy, the belief that past events influence the likelihood of future ones, even when they're completely independent. The logic seems intuitive. If something hasn't happened in a while, it's due to happen soon. But in reality, probability doesn't work that way. The roulette wheel doesn't have a memory. Each spin is just as random as the last. Our brains love spotting patterns, even when none exist. That's why people think a coin flip that lands on heads 5 times must be more likely to land on tails next, even though the odds are still 50-50 every time. This fallacy fuels bad bets, from casinos to stock markets, to everyday decision-making. Think about it. How often do people say things like, "It hasn't rained in weeks, so we must be getting a storm soon," or, "I failed 3 job interviews in a row, so I'm bound to get the next one." These assumptions feel right, but they aren't based on actual probability. Each event is independent, and the universe doesn't keep a tally. Casinos and lotteries thrive on this faulty thinking. Ever heard of the martingale strategy? It's the classic trap where gamblers keep doubling their bets, thinking they're bound to win eventually, but without infinite money, all it takes is a long losing streak to wipe someone out completely. So how do you avoid falling for the gambler's fallacy? First, recognize when you're expecting a pattern that isn't there. Second, understand that independent events don't have memory, whether it's dice, stocks, or the weather. Past outcomes don't dictate the future. And finally, trust the math, not your gut. Just because something feels overdue doesn't mean it actually is. Next time you catch yourself thinking, "It has to happen this time,"
Take a step back. Are you seeing a real pattern, or is your brain just playing tricks on you? Lottery paradox. When winning feels impossible and certain at the same time, imagine you're holding a lottery ticket. You know that the chances of winning are 1 in a million, so small that it seems impossible, but at the same time, you also know that someone will win, and if someone has to win, why not you? That contradiction, believing both that winning is nearly impossible and that someone is bound to win, is what makes the lottery paradox so fascinating. The paradox was first proposed by philosopher Henry Keiberg to challenge how we think about rational belief. If you're thinking logically, you should believe that your ticket won't win, because the odds overwhelmingly support that conclusion. But if you apply that logic to every ticket, then you end up believing that no one will win, which contradicts the fact that a winner must exist. So what do you believe? It's the same reasoning we use in everyday life. Take job applications. If 500 people apply for a position, each person individually seems unlikely to get hired, but we also know that someone will get the job. Or consider legal trials. If every juror believes there's a small chance that a witness is mistaken, does that mean the entire testimony should be dismissed as unreliable? The paradox shows that when we deal with large sets of possibilities, our usual way of thinking breaks down. This also connects to how people make decisions. Some avoid playing the lottery because the odds feel impossible. Others play because they fixate on the fact that a winner is inevitable. The same paradox applies to risk-taking in investments, career choices, or even relationships, where the likelihood of success seems slim, but people move forward anyway because, well, someone has to succeed. So how do you resolve the lottery paradox? One approach is to reconsider how we handle belief and probability. Just because something is overwhelmingly unlikely doesn't mean it's impossible, and just because an event must happen to someone doesn't mean it has to happen to you. The key is balancing statistical reality
with practical decision-making. Next time you find yourself torn between thinking something is impossible yet inevitable, ask yourself, are my beliefs contradicting themselves? Or am I just seeing probability in a new way? Paradox of voting. Why do we vote if it barely matters? You wake up on election day, and the question hits you, should I even bother voting? After all, what are the odds that your one vote will decide the outcome? In a national election with millions of voters, that chance is practically zero. So if voting is irrational, from a purely mathematical standpoint, why do so many people still do it? This is the paradox of voting, also known as Downes's paradox, and it reveals a strange contradiction. If people were purely rational decision makers, most of us would skip voting entirely, because the cost of voting, time, effort, inconvenience, far outweighs the probability of influencing the result. Yet in every election, millions of people still turn up at the polls. Why? One reason is that humans aren't just cold, calculating machines. We don't just vote to win, we vote because of a sense of civic duty. The act of voting makes people feel engaged, responsible, and part of something bigger. There's also the idea of group impact. While one vote is insignificant, the collective action of many individuals does shape elections. If everyone thought, my vote doesn't matter, then no one would vote, and democracy would collapse. This paradox extends beyond politics. Why do fans cheer for their team at a stadium, knowing their voice won't change the game? Why do people donate to large charities, even when their contribution alone won't solve the problem? The answer lies in psychology over pure logic. We engage in these actions because they connect us to a shared purpose. Another way to resolve the paradox is to look at voting not as an isolated act, but as a long-term strategy. If you only voted once in your life, maybe it wouldn't matter. But if you and your community consistently participate, you contribute to gradual political shifts over time. Voting isn't just about one election, it's about shaping the future. So the next time someone says, one vote doesn't matter, ask yourself, are they looking at the full picture, or just the immediate numbers? Because while a single vote might be small, democracy itself is built on the idea that every vote together makes a difference.
Brace's Paradox. When more choices make things worse, you've been stuck in traffic for what feels like forever. You inch forward, slam the brakes, inch forward again. Frustrated, you think, if only they built another road, this wouldn't be happening. More roads should mean less congestion, right? But what if I told you that adding an extra road can actually make traffic worse? It sounds absurd, but that's exactly what happens in Brace's Paradox, a counterintuitive reality where giving people more options creates more problems instead of solving them. Picture a city with two main routes from one side of town to the other. Some drivers take the highway, faster but easily clogged, while others use side streets, slower but more consistent. Traffic moves smoothly enough because drivers naturally split between the two. Now imagine city planners decide to add a shortcut, a high-speed connector between the two routes. Logically, this should reduce travel times, but instead, it backfires spectacularly. The shortcut is so appealing that everyone flocks to it, believing they've found a faster way, but as more cars pile onto the new route, unexpected bottlenecks form. The careful balance that once kept traffic moving is destroyed. Now, every road is jammed, and everyone's commute takes longer than before. It's like a brand new grocery store checkout lane opening up, only for every customer to rush to it at once, slowing everything down instead of speeding things up. This happens because people make decisions based on what's best for them individually, without considering the larger system. Each driver is focused on getting ahead, but when everyone makes the same choice, it backfires. More choices don't always mean better outcomes. Sometimes they create chaos. We've seen this paradox unfold in big cities like New York and Seoul, where removing certain roads actually improved traffic flow. It happens in networking too. Sometimes increasing bandwidth slows down internet speeds due to inefficient data routing. Even in sports, a superstar player added to a team can disrupt chemistry, leading to worse overall performance. So how do we avoid this? Smarter planning. Instead of simply adding more, traffic engineers run simulations to see how changes will actually impact flow. Some cities remove roads or introduce tolls to control congestion. Apps like Google Maps help by guiding drivers away from overloaded routes in real time. And beyond traffic, this paradox teaches us an important lesson. More options aren't always better. In business, relationships, or problem solving, sometimes cutting back leads to better results. Next time you're stuck in traffic, don't just wish for more roads. Ask yourself if maybe, just maybe, the best way forward is fewer. Abilene Paradox. When everyone agrees but no one wants it. Ever said yes to something you didn't actually want, just because you assumed everyone else did? You're not alone. Picture this, it's a scorching summer day in Texas, and a family is relaxing in the shade. Someone casually suggests a road trip to Abilene for dinner, a 50-mile drive in the unbearable heat. Nobody really wants to go, but one by one they agree, because each person assumes the others are excited about it. After hours of sweat, exhaustion, and mediocre food, they return home, only for someone to admit, "I didn't actually want to go." To their shock, everyone else says the same thing. This is the Abilene Paradox, a bizarre twist in human behavior where a group ends up making a decision that none of its members actually wanted, not because of pressure, not because of persuasion, but because everyone wrongly assumes they're the only one who feels differently. It's not just a quirky family story. This happens everywhere, from corporate boardrooms to friend groups trying to pick a restaurant. The fear of rocking the boat makes people go along with a bad choice, leading to wasted time, frustration, and regret.
Why does this happen? One reason is pluralistic ignorance, the assumption that everyone else is on board, when in reality, they're just as hesitant. Then there's fear of rejection, that nagging worry that speaking up will make you seem difficult or out of sync with the group. Instead of voicing concerns, people stay silent, and the cycle of false agreement continues. It plays out in workplaces all the time. A management team moves forward with a risky expansion because everyone assumes their colleagues support it, even though deep down, no one actually thinks it's a good idea. Governments push policies based on the mistaken belief that the public wants them. Even something as simple as choosing a movie with friends can fall victim to this paradox. Everyone sits through 2 hours of a film no one really wanted to watch, just because they thought it was someone else's pick. So how do you stop falling into this trap? The simplest way is to speak up. Instead of assuming, ask, does everyone actually want this, or are we just going along with it? Creating an environment where honest opinions are welcome makes a huge difference. Companies can introduce anonymous feedback to gauge real preferences. Teams can assign a devil's advocate to challenge decisions and make sure all voices are heard. And most importantly, recognizing that disagreement isn't a bad thing can save everyone from regret. Next time you find yourself nodding along to something you're not thrilled about, take a second and ask yourself, am I actually choosing this, or am I just assuming everyone else wants it? You might not be alone in wanting to take a different path. Prisoner's dilemma, the paradox of rational decision-making. Imagine you and a close friend are arrested for a crime you didn't exactly commit. The police separate you into different rooms and offer both of you the same deal: betray your friend, to go free, or stay silent, and risk serious jail time. You have no way of knowing what your friend will do. If you both stay silent, you each get a light sentence. If you both betray each other, you both get a heavier sentence. But if one of you stays loyal while the other snitches, the traitor walks free, and the loyal one takes the full hit. What do you do? This is the prisoner's dilemma, a mind-bending paradox that shows how acting in your own self-interest can lead to the worst possible outcome for everyone. On the surface, snitching seems like the smartest move. No matter what the other person does, betraying them either gets you out, or at least reduces your sentence. But here's the twist: if both of you think this way, you both end up worse off than if you had just trusted each other. It's not just a hypothetical game. We see this dilemma play out all around us. Nations stockpile nuclear weapons, fearing the other side will attack first. Businesses slash prices to undercut competitors, even though it leads to lower profits for everyone. People overfish or pollute, because they assume others will do it anyway. The logic that drives individuals to protect themselves often creates collective disaster. So why does this happen? The problem is trust, or rather, the lack of it. If you knew for certain that your friend would stay silent, you'd do the same, and both of you would get the best possible outcome. But without that certainty, fear takes over. The worst-case scenario, being the only one left holding the bag, outweighs the logical best-case scenario. People don't always make the smartest decision for the group when they can't rely on others to do the same. Now, what if this wasn't a one-time game? What if you had to make this choice over and over again, knowing that your past actions influence what happens next? That's called the iterated prisoner's dilemma, and here's where things get interesting. When played multiple times, people begin to realize that constant betrayal leads to mutual destruction. Instead, cooperation emerges as the best long-term strategy, the tit-for-tat approach, where you start by trusting, then copy whatever the other player did last time, often leads to the most success. It rewards cooperation, but punishes betrayal, building trust over time. This applies to real-world problems like environmental conservation, business competition, and even personal relationships. If you always act selfishly, people will eventually stop trusting you. But if you show you're willing to cooperate, others will too, leading to better outcomes for everyone. So the next time you're faced with a tough choice, act selfishly, or take a risk on trust. Think about the bigger picture. Are you setting yourself up for a temporary win, or are you making decisions that could lead to long-term success? The prisoner's dilemma teaches us that sometimes, the smartest move isn't just looking out for yourself, it's looking out for each other.
Allais Paradox.
Why we make irrational choices. Imagine you're offered a choice. You can take a guaranteed $1 million right now, or you can gamble. There's a 10% chance you'll win $5 million, an 89% chance you'll still get $1 million, and a 1% chance you'll walk away with nothing. What do? Most people grab the guaranteed million. It feels safe, logical. But now, let's change the game. This time, your choices are different. An 11% chance at $1 million, or a 10% chance at $5 million. Suddenly, most people chase the bigger prize, even though the math behind both scenarios is nearly identical. Why do our brains flip? That's the Allais Paradox, a mind-bending contradiction in decision-making that reveals just how irrational we are when it comes to risk. We love certainty. A guaranteed win feels far more valuable than a gamble, even when that gamble could technically be the better choice. It's called the certainty effect, and it's why we tend to overvalue things that feel like a sure thing. This is also why people overpay for insurance, not necessarily because it makes financial sense, but because the thought of having even the smallest chance of losing everything is terrifying. It's why gamblers chase massive jackpots with terrible odds, but hesitate to make smart, calculated investments. And it's why some patients choose less effective, but guaranteed treatments over riskier, more effective ones. The problem is, our brains don't weigh probabilities correctly. We exaggerate tiny chances, ignore large ones, and let emotion override logic. Seeing $5 million makes us dream big, but hearing 1% chance of nothing makes us panic. So, how do we stop falling for it? First, think in terms of expected value. Don't just look at certainty. Ask yourself what the long-term outcome would be if you made the same decision 100 times. Second, beware of the certainty trap. Just because something is guaranteed doesn't mean it's the smartest choice. And finally, challenge your instincts. That gut feeling pushing you toward the safer bet, it might not actually be working in your favor. The Allais Paradox proves that our brains aren't wired for perfect logic. We crave security and avoid regret, even when it leads to irrational choices. But now that you know the trick, you can start spotting it in your own life. So, next time you're making a big decision, ask yourself, am I thinking clearly, or am I just chasing the illusion of certainty? Simpson's paradox. When the numbers deceive you, you're looking at two job candidates. Candidate A outperforms Candidate B in both technical and managerial roles. Seems like an easy choice, right? But then, when you combine the numbers, Candidate B somehow comes out on top. How does that happen? Imagine a university reviewing admission rates. In one department, men have an 80% acceptance rate, while women have 60%. In another department, men have 30%, while women have 20%. Clearly, men are being admitted at higher rates in both cases, but when the data is combined, something strange happens. Women now have a higher overall acceptance rate. How is that possible when they had a lower rate in both individual groups? This is Simpson's paradox, a statistical illusion that flips trends upside down. The trick lies in how the data is grouped. If more women applied to the highly competitive department with fewer available spots, while more men applied to an easier one, the final numbers get distorted. It's not about who had better odds, it's about where they applied. These kinds of statistical traps appear everywhere. A new medical drug might appear to work well for younger patients and older patients separately, but when data is combined, it looks ineffective. A basketball player might have a higher shooting percentage in both halves of a season, but a lower average overall. A company might seem to favor male hires when looking at total numbers, but a deeper dive could reveal that women were simply applying to more competitive departments. So how do you avoid getting fooled? Always examine subgroups separately. Ask yourself if there's a hidden variable affecting the results. Be cautious with averages. When group sizes differ, they can create misleading trends. And most importantly, don't trust summary statistics at face value. Numbers might seem objective, but without context, they can lead to false conclusions. Next time you see a big claim based on data, take a second look. Are you really seeing the full picture, or is this just another case of misleading math? Parendo's paradox. When losing makes you a winner, what if two losing strategies, when combined, could actually lead to a winning outcome? Sounds impossible, right? But that's exactly what Parendo's paradox proves. It's a bizarre yet fascinating concept in probability and strategy that shows how failure, when structured correctly, can lead to success. Imagine you're playing two different games. The first, Game A, is a coin toss, where you lose slightly more often than you win. The second, Game B, is a trickier game that also favors the house, but has small windows where winning is possible. Play either game on its own, and you're bound to lose in the long run. But something strange happens when you alternate between them in the right sequence. Suddenly, you start winning. Two losing games, when played together in a strategic pattern, create a winning outcome. It's like climbing a mountain by taking 2 steps back and 3 steps forward. One move alone won't get you there, but the right combination propels you upward. This works because of non-linear dynamics. In simple terms, the whole is greater than the sum of its parts. Game A slowly depletes your resources, keeping you at a disadvantage. Game B, despite being a losing game, has small moments of opportunity. If played at the right times, it offsets the losses from Game A. The alternating sequence exploits small advantages that wouldn't exist in isolation. This same principle plays out in real life. Investors mix high-risk and low-risk strategies to balance losses and gains, creating steady growth over time. Athletes alternate between intense training that breaks muscles down and recovery periods that build them back stronger. Businesses sacrifice short-term profits to invest in long-term innovation, ultimately leading to greater success. Even in nature, some species cycle between two inefficient survival strategies, but together they increase their chances of thriving. So how can you use this in your own life? First, don't fear small losses. They might be setting you up for a bigger win. Balance your approach instead of relying on one method. Time your moves wisely, since success often depends not just on what you do, but when you do it. Experiment and adapt, because trial and error is how many of the world's most successful systems operate. Parendo's paradox reveals that sometimes, losing is the key to winning. What looks like failure in isolation can actually be part of a greater path to success. The next time you feel like you're losing, ask yourself, am I really failing, or am I just setting myself up for my next move?
The Fermi Paradox. Where is everyone? Look up at the night sky. Billions of stars stretch across the cosmos, each potentially surrounded by planets teeming with life. Given the sheer number of planets, logic suggests that intelligent civilizations should be out there, thriving, building, exploring, maybe even colonizing entire galaxies, and yet, as far as we can tell, space is silent. No signals, no visitors, no grand evidence of alien life. This is the Fermi Paradox. The baffling contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for them. Physicist Enrico Fermi famously posed the question in the 1950s, where is everybody? If life is common, why haven't we found even a whisper of another intelligent species? Since then, countless theories have tried to explain this cosmic mystery. One possibility is that intelligent civilizations destroy themselves before they can spread across the stars. Maybe advanced species inevitably fall to nuclear war,
ecological collapse, artificial intelligence, or something we haven't even imagined. This idea is called the Great Filter Hypothesis, the notion that somewhere along the path from simple life to interstellar travel, there's an almost impossible hurdle that prevents civilizations from surviving long enough to make themselves known. If the Great Filter is ahead of us, that's bad news. It could mean humanity is doomed to self-destruction before reaching the stars. But what if the Great Filter is behind us? Maybe the conditions for life are far rarer than we assume. Perhaps Earth is incredibly special, one of the only places where life made it past the microbial stage. If that's the case, we might be among the first intelligent beings to emerge in the universe, a terrifying but exhilarating possibility. Another explanation is that alien civilizations are deliberately staying silent. The dark forest hypothesis suggests that the universe is like a vast, shadowy jungle, where civilizations hide in fear of being detected. Just like prey animals stay quiet to avoid predators, intelligent species may choose to remain unseen, fearing the possibility of hostile forces. If this is true, making too much noise, like broadcasting signals into space, might be the worst mistake we ever make. Or maybe we're simply looking in the wrong way. What if alien civilizations don't use radio signals? What if their methods of communication are beyond our comprehension, neutrinos, quantum entanglement, or something even stranger? It's possible the universe is buzzing with alien messages, but we just don't know how to listen. And then, there's the eerie thought that aliens have already visited, but long before humans even existed. Perhaps life on Earth was influenced by ancient travelers who left no obvious trace. Or maybe we are the aliens, the descendants of a long-lost interstellar migration we no longer remember. So what do you think? Is the universe empty, or is it filled with civilizations hiding in the shadows? Have we simply not searched hard enough, or is there something preventing us from finding our cosmic neighbors? Until we discover definitive proof, the Fermi Paradox remains one of the greatest mysteries of our existence, one that keeps us looking up, wondering, waiting, and listening for an answer that may never come.
The Drake equation. Estimating the odds of alien life. What if the universe is teeming with life, but we simply haven't found it yet? For centuries, humans have gazed at the stars and wondered if we are alone. With billions of stars in our galaxy and even more planets orbiting them, it seems almost inevitable that intelligent civilizations should exist. Yet, despite all our searching, we have found no undeniable proof of extraterrestrial life. This question, how many alien civilizations might be out there, is what Drake's equation attempts to answer. In 1961, astrophysicist Frank Drake formulated this equation to estimate the number of technologically advanced civilizations in our galaxy that might be capable of communicating with us. It considers key factors, including the rate at which new stars form in the Milky Way, the fraction those stars that have planets, the number of planets per star that could support life, the probability that life actually develops on those planets, the likelihood of life evolving into intelligent beings, the fraction of intelligent civilizations that develop technology capable of interstellar communication, the length of time such civilizations remain detectable. While the equation provides a structured way to think about extraterrestrial life, it relies heavily on unknowns. Some values, like the number of planets in the habitable zone, can be estimated based on current astronomical discoveries, but others, such as the likelihood of intelligent life forming, remain purely speculative. Depending on the numbers we input, Drake's equation can suggest vastly different outcomes. An optimistic estimate might indicate thousands or even millions of intelligent civilizations in the Milky Way. A more pessimistic approach could mean we are the only ones. The uncertainty leaves us with a tantalizing mystery. Are we one of countless civilizations,
or a rare anomaly in the vastness of space. One of the most compelling aspects of Drake's equation is how it transforms an abstract curiosity into a scientific framework. Each breakthrough in exoplanet research, astrobiology, and even artificial intelligence helps refine our understanding of the factors in the equation. It guides our search, whether through scanning the skies for alien radio signals, analyzing atmospheric compositions of distant planets, or studying extreme environments on Earth to understand how life might exist elsewhere. But even if Drake's equation tells us that intelligent life should be abundant, it doesn't answer the biggest question: where are they? Have they chosen to remain silent? Are they too far away for us to detect, or is the universe far lonelier than we ever imagined? Until we make contact, the numbers remain just that, numbers. The real answer still waits among the stars, just beyond our reach, whispering possibilities of worlds yet to be discovered.
The causal loop paradox. A time loop with no beginning. Imagine waking up one day to find a note on your desk, handwritten but unsigned, warning you about an event that will change your life forever. You follow the advice on the note, and it saves you from disaster. Years later, after learning about time travel, you travel back to the past and write that very same note for your younger self. Now, think about it. Who originally wrote the note? Did it ever have a true beginning? Or is it stuck in a never-ending cycle of cause and effect? Welcome to the causal loop paradox, a perplexing time travel scenario where events cause themselves in a closed cycle with no clear origin. This paradox, also called a closed time-like curve, occurs when an event in the past is caused by an event in the future, which was in turn caused by the original past event. The problem: there is no real starting point. The cause and effect feed into each other in an infinite loop, making it impossible to pinpoint where it all began. One of the most famous examples of this paradox comes from science fiction. Imagine a scientist from the future who wants to preserve a groundbreaking formula. They travel back in time and give the formula to a young scientist. That young scientist then studies it, refines it, and eventually becomes the very scientist who years later travels back in time to pass on the formula. The information exists in an endless cycle, but who actually discovered it in the first place? There's no true origin, just an eternal loop of repetition. The paradox doesn't just apply to information. What if a time traveler brings back a historical artifact, like an ancient book, and gives it to a famous writer? The writer then copies it and publishes it as their own work. Centuries later, the time traveler finds the published book and brings it back to the past, ensuring the cycle continues. But where did the book actually come from? Did it ever have a real author? This paradox challenges our understanding of time and causality. Normally, every event has a cause, and every cause precedes its effect. But in a causal loop, the cause and effect become one and the same, looping infinitely. So, how can this paradox be resolved? Some physicists argue that it's possible under the right conditions. The Novikov self-consistency principle suggests that time travel might work as long as events within the loop are consistent, meaning that anything a time traveler does in the past was always meant to happen. In other words, if the formula was given to the young scientist, then history will always unfold in a way that ensures the loop remains intact. Another possibility is that the object or information is simply uncreated. It exists without an origin, supported by time itself. If time travel were real, the universe might allow such loops as long as they remain stable. This raises deeper philosophical questions. Can something exist without being created? Is it possible for knowledge or objects to sustain themselves purely through time loops? A third explanation is the multiverse theory, which suggests that these loops don't exist in our universe alone. Instead, they might span across different timelines, where an event that appears to be originless in one reality actually has a clear beginning in another. Under this theory,
time travelers might be borrowing from an alternate reality, even if it seems like a self-contained loop in their own timeline. The causal loop paradox forces us to rethink how time functions. If time travel were ever proven possible, would we encounter stable time loops? Could we send ourselves knowledge from the future with no real origin? And if such loops exist, what does it mean for our understanding of free will? Are we truly making our own choices, or are we just following a predetermined cycle that was always meant to happen? If you were given information from the future, maybe winning lottery numbers, a cure for disease, or even the answer to life's biggest mysteries, would you use it? And if you did, would you one day find yourself traveling back to the past to pass on the same knowledge, continuing the loop? The causal loop paradox is more than just a theoretical mystery. It's a challenge to everything we think we know about time, cause, and existence itself.
The Bootstrap Paradox, a mystery without a beginning. Have you ever come across a story, an object, or an idea that seems to exist without a clear origin, something that appears in history, but has no true creator? Imagine picking up a book, traveling back in time, and handing it to a famous writer before they ever wrote it. The writer then publishes the book, and it becomes widely known. But where did the book really come from? Who actually wrote it? This strange conundrum is known as the Bootstrap Paradox, a time travel mystery that defies logic and questions the very nature of cause and effect. This paradox gets its name from the phrase, pulling yourself up by your own bootstraps, which means achieving something impossible without any external help. In the case of time travel, an object, piece of knowledge, or even a person can exist in an endless loop, with no point of creation, only perpetual existence. It's like reality, playing a game of infinite recycling, where something exists simply because it always has. Let's take another example. Suppose a scientist from the future discovers a groundbreaking equation that changes physics forever. Wanting to ensure its legacy, they travel back in time and give it to a young physicist, the same one who was credited with discovering it in the first place. That physicist writes it down and shares it with the world. But where did the equation originally come from? If the scientist from the future only knew it because they read it in a book that was written based on their own future self's knowledge, then who actually invented it? The information is stuck in a self-contained loop, without an actual point of origin. The Bootstrap Paradox isn't just about equations and books, it applies to any situation where something seems to exist without being created. A classic example in fiction is the story of a time traveler who goes back in time and gives a young Beethoven his own future compositions, ensuring that history unfolds as expected. But if Beethoven only wrote the music because he was given it, then who originally composed it? These paradoxes challenge our understanding of time and causality. Normally, we assume that every effect has a cause, every creation has a creator, but in bootstrap scenarios, the chain of cause and effect is broken, looping endlessly, with no clear beginning. It's as if something just is, defying the fundamental rules of logic. So how do we resolve this paradox? Scientists and philosophers have proposed several possibilities. One idea is that the information, object, or idea in the loop is self-created and does not require an external origin. This means that the paradox isn't really a paradox, it's simply how time works in cases of temporal loops. If reality allows for stable time loops, then these objects can exist without ever being created in the traditional sense. Another explanation suggests that these events only occur in alternate timelines or universes. Under the multiverse theory, every action in time travel creates a new branch of reality. This could mean that the book, equation, or song was created in an entirely different timeline, but when it was brought into the past, it entered a loop where its original timeline
was no longer needed. Some theories even suggest that time itself has built-in mechanisms to prevent these paradoxes from occurring. Maybe, if you try to create a bootstrap loop, the universe will subtly intervene, introducing small changes that break the cycle and restore normal cause and effect relationships. At the heart of the Bootstrap Paradox is a deep question: can time loops allow information or objects to exist without a true beginning? If so, does that mean that knowledge and creation can be borrowed from time itself, rather than originating from a single point? This paradox forces us to reconsider our understanding of reality. If time travel were possible, would we be able to create something without ever inventing it? Would we be able to send back ideas that never had an original creator? It's a mind-bending thought, and one that continues to spark debate among physicists, philosophers, and science fiction fans alike. So, if you had the power to send something back in time, an idea, a book, or even yourself, what would you choose? And if you did, would it truly be yours, or just another part of an endless cycle with no real beginning? The Bootstrap Paradox remains one of the strangest mysteries of time travel, a riddle without an answer, a loop without an origin, forever challenging our perception of time and existence.
The Grandfather Paradox, a journey into time travel's most baffling mystery. Imagine stepping into a time machine, setting the dial to decades before your birth, and arriving in an era where your own existence hangs in the balance. What if, by accident or design, you prevented your grandfather from meeting your grandmother? Would you suddenly vanish from existence? Would the universe correct itself? Or would reality crumble into chaos? This mind-bending dilemma is known as the Grandfather Paradox, and it's one of the most intriguing thought experiments in time travel theory. Time travel has long captured our imagination. Stories of adventurers, scientists, and thrill-seekers venturing into the past or future fill books, movies, and endless late-night debates. But when it comes to changing the past, things get complicated fast. If you traveled back and altered a key event in your family history, what would happen to you? If your own birth was erased from the timeline, how could you have traveled back in the first place? The paradox is a loop with no clear escape. It doesn't just apply to family history. What if a scientist went back in time and prevented the discovery of a world-changing invention, or a musician taught a song from the future to a composer of the past, creating a melody with no clear origin? These paradoxes challenge our understanding of logic, cause, and effect. So, how can the Grandfather Paradox be resolved? Some scientists propose that history is self-correcting. No matter what you do, events will always find a way to play out as they were meant to. Maybe your grandfather still meets your grandmother under different circumstances. Maybe the gun jams, or fate throws another curveball to keep the timeline intact. This idea, known as the Novikov self-consistency principle, suggests that time travel might be possible, but changing history is not. Another theory suggests that each action creates a new branching timeline. Under the multiverse theory, if you stop your grandfather from meeting your grandmother, you don't erase yourself from existence, you just shift to an alternate reality where you were never born. Meanwhile, in your original timeline, nothing has changed, and you continue to exist. This would mean every action in time travel spawns a new reality, leading to infinite parallel worlds. But what if the universe simply prevents paradoxes from happening at all? The restricted action hypothesis proposes that something, whether physics, fate, or an unknown force, prevents you from making changes that would create contradictions. Perhaps your attempts to alter the past always fail, ensuring consistency in the timeline. If you tried to interfere, circumstances beyond your control would stop you, maintaining the flow of history. Others suggest that time might be flexible in ways we don't yet understand. Could paradoxes resolve themselves through temporal feedback loops, where changes still lead to the same outcome in an unexpected way? Maybe your actions in the past actually caused the events you were trying to prevent, rather than stopping them. These theories raise bigger questions.
Is time travel even possible? If so, does it mean we live in a deterministic universe where everything is already set in stone, or do we have free will to change our past, and by extension our future? Physicists have debated the mechanics of time travel for years, with Einstein's theories hinting that bending time might not be entirely out of reach. Yet for now, practical time travel remains firmly in the realm of speculation. What we do know is that the grandfather paradox continues to challenge our understanding of time, causality, and existence itself. So if given the chance, would you dare to change the past, or would you be content to observe history unfold, knowing that even the smallest action could unravel everything? The mystery of time travel may never be solved, but one thing is certain: this paradox will keep us wondering for generations to come.
Maxwell's demon, cheating the laws of thermodynamics. Imagine you're standing in front of two rooms connected by a tiny door. One room is hot, the other is cold. Now, what if you had a tiny invisible helper who could control that door, only letting fast-moving hot particles into one room and slow-moving cold particles into the other? Over time, the hot room gets hotter, the cold room gets colder, and you've just broken the second law of thermodynamics. Or have you? Welcome to the paradox of Maxwell's demon. This thought experiment was proposed by Scottish physicist James Clerk Maxwell in 1867. It was designed to challenge one of the fundamental principles of physics, the second law of thermodynamics, which states that entropy, disorder, always increases in a closed system. In other words, energy naturally spreads out, heat moves from hot to cold until everything evens out. But Maxwell wondered, what if we could cheat this rule? Let's meet the so-called demon. Picture an incredibly tiny, intelligent being who can see individual gas molecules moving around. When a fast-moving hot molecule approaches the door, the demon quickly opens it, letting it into one room. When a slow-moving cold molecule approaches, the demon only lets it into the other room. Over time, one side becomes hotter and the other becomes colder, effectively reversing entropy without expending any energy. This seems like a direct violation of thermodynamics. It creates a temperature difference for free. If real, it would allow for perpetual motion machines and endless energy generation. But physicists knew something had to be wrong. The catch: the demon itself needs energy to function. If the demon is measuring particles, opening doors, and keeping track of movement, it must use some form of energy, and that energy costs entropy. In the 20th century, physicists realized that the act of information processing is tied to thermodynamics. In 1961, Rolf Landauer showed that erasing information, a necessary step for the demon to keep track of particles, creates heat. This means that even if the demon is cheating in the short term, the overall entropy of the system still increases when considering its memory and decision-making process. So, does Maxwell's demon truly break physics? Not quite. The paradox helped scientists realize that information is physical, and even knowledge comes with a thermodynamic cost. This insight has led to breakthroughs in fields like quantum computing, where the connection between information and energy plays a crucial role. In the end, Maxwell's demon didn't break the laws of physics. It expanded our understanding of them. It showed us that reality isn't just about energy and matter, but also about information itself. And maybe, just maybe, the universe is far stranger than we ever imagined. Schrödinger's cat. The paradox of quantum superposition. Imagine you're handed a box. Inside there's a cat. But before you open it, I have to ask, is the cat alive or dead? You might think there's an easy answer. Either it's breathing, or it isn't. But according to quantum mechanics, the answer is both. Welcome to the mind-bending paradox of Schrödinger's cat, a thought experiment designed to challenge our very understanding of reality. Picture this: a sealed box containing a cat, a radioactive atom, a Geiger counter,
a vial of poison, and a hammer. The atom has a 50% chance of decaying within an hour. If it decays, the Geiger counter detects it, triggering the hammer to shatter the poison vial, which then kills the cat. If the atom doesn't decay, the cat stays alive. But here's where things get strange. Until you actually look inside the box, quantum mechanics says the atom is in a superposition of both decayed and not decayed states. And if the atom is in two states at once, so is the cat. That means, in some eerie way, it's both alive and dead at the same time. It only becomes one or the other when you open the box and observe it. How can that be? In classical physics, things have definite states, whether we look at them or not. A ball is either rolling or still. A light is either on or off. But quantum mechanics doesn't work like that. Subatomic particles can exist in multiple states at once until they are observed. The cat's fate, bizarrely enough, hinges on this principle of quantum superposition. But wait, does that mean reality itself depends on observation? That's where the interpretations come in. The Copenhagen interpretation, one of the most widely accepted views, argues that the cat exists in a superposition of states until an observer collapses the wave function into a definite reality, alive or dead, but not both. It suggests that measurement fundamentally changes reality. But then there's the many worlds interpretation, the ultimate science fiction dream. This theory proposes that instead of collapsing into one outcome, reality actually splits into two. In one universe, you open the box and see a live cat. In another, you find a dead one. Every quantum event creates a branching of realities, meaning there's an infinite number of universes constantly forming from every possible decision and outcome. Schrödinger never meant for this paradox to be taken literally. He created it to showcase how absurd quantum mechanics can seem when applied to everyday objects. In the real world, we don't see things existing in multiple states at once because of a phenomenon called decoherence, which prevents macroscopic objects from behaving like quantum particles. But that doesn't mean the implications of this paradox aren't very real. Today, quantum superposition isn't just a thought experiment, it's the foundation of cutting-edge technology. Quantum computing harnesses this principle, allowing qubits to exist in multiple states at once, exponentially increasing computational power. Scientists are also exploring whether quantum biology plays a role in natural processes like photosynthesis, or even bird migration. So, does the universe only take shape when we look at it? Are we collapsing reality just by observing it? The answer isn't clear, and maybe it never will be. But one thing is certain, Schrödinger's cat has forever changed the way we think about the very nature of existence, and maybe, just maybe, reality is a little stranger than we ever imagined.
Twin paradox. Aging at different speeds. Imagine you have an identical twin. One day, they hop into a spaceship, accelerate to near the speed of light, and zoom off into space while you stay on Earth. When they finally return, something shocking has happened. You've aged decades, but they've barely aged at all. How is this possible? Welcome to the mind-bending world of the twin paradox, a thought experiment that challenges our very perception of time. The paradox is rooted in Einstein's theory of relativity, which states that time isn't constant, it changes depending on how fast you're moving. The faster you go, the slower time passes for you compared to someone who's standing still. This is called time dilation, and at everyday speeds, we don't notice it, but at relativistic speeds, close to the speed of light, time slows down dramatically. Now, let's break down why this happens. According to special relativity, an observer in motion will experience time at a different rate than an observer at rest. In our scenario, the twin on the spaceship is moving at an extreme velocity, meaning their clock is ticking much more slowly than the twin who stayed on Earth. By the time the traveling twin returns, Earth has aged significantly more than they have. But wait, if all motion is relative,
Couldn't the astronaut twin argue that they were stationary while Earth was the one moving? Shouldn't both twins experience the same time dilation? This is where the paradox comes in. The key lies in acceleration. Special relativity applies to constant motion, but the traveling twin must accelerate to leave Earth, decelerate to turn around, and accelerate again to return home. These changes in velocity make their experience different from the twin who remained at rest. The moment acceleration is involved, the situation is no longer perfectly symmetrical. This paradox isn't just theoretical, it's been tested. Scientists have sent highly accurate atomic clocks on airplanes and satellites, and guess what? The moving clocks tick slower than those on Earth, exactly as relativity predicts. GPS satellites even have to account for this effect to maintain accuracy. So does this mean astronauts could travel to the future by flying close to the speed of light? Technically, yes. If a human were to travel at relativistic speeds for what felt like a few months, centuries could pass on Earth. While we're far from achieving such speeds, this paradox reminds us that time is not an absolute, it's relative to motion. The twin paradox isn't a flaw in physics, it's a demonstration of just how strange and flexible time can be. So if your dream is to see the distant future, you might just need a really fast spaceship.